probably fix that before starting the presentations. You're currently on mute.
I think that should be resolved now. Yeah, I apologize. I had it muted for the beginning discussion, so before we actually kicked off. So
yeah, so Daniel, maybe let's just get quickly through the agenda, like just like an overview of the agenda, and maybe this can kind of start some discussion. Michał, can you say a couple words about your presentation?
Sure. So
and if you can like lower the sensitivity of the mic, because it's like it's
loud.
Like very,
how about now?
Yeah, that's way better.
Okay. So so to give you some short agenda about my presentation, I'll be talking mainly about DRTM. How does it work for AMD and Intel processors? And I'll try to show some examples of TrenchBoot on ASUS KGP D16 and Dell Optiplex 9010, as well as I will compare how those two implementations of DRTM work and what are the pros and cons.
Mm-hmm. So I believe, like in your presentation, what would be interesting is perspective of firmware and how like complex from firmware developers' perspective is to integrate given the RTM technology, given implementation of the RTM technology.
Yes, and I will also be focusing mainly on open source firmware.
Yeah. Yeah. So next presentation will be two main presentations. One will be about FOBnail. So FOBnail is a NLNet Foundation sponsored granted project, which has the goal of creating reference open source firmware implementation for USB token or USB crypto tokens. And this would be implementation of attestation server, which can be used in connection with the RTM technology to attest platform and like dynamically launched measured environment on the platform. So I believe like a couple of people recently asked about this kind of capability. Even I saw on Twitter that some people were interested in Bluetooth version of such mechanism. So yeah, I hope we will have interesting discussion about ability of attesting platform without external internet connectivity, external connectivity to the servers, just over the USB and just using server which is on the USB crypto token. So that would be FOBnail. And then next presentation would be LVFS host security ID, where we will discuss project Linux Foundation project LVFS FWPD. Especially we will discuss one of the feature, which is host security ID. This feature is for quickly evaluating security of the platform. This is mainly for end users. So it do the checks, what kind of security capabilities are enabled, and looking at the report of, looking at the HSE, we can say like what kind of security features are enabled and easily judge how secure is this platform. And from our perspective, why it is interesting, because we're thinking about what kind of tests we should add to make sure the RTM is evaluated correctly, like what we have to test to make sure that the RTM works well on given platform. And I believe this is a lot of details with that, and that will be discussion after. And then I believe Stuart will talk a little bit. Stuart, yeah. Can you say a little bit about your presentation?
Yeah, I'm going to give an update on DRTM on ARM, which is the architectures in development, just where we are with. I mean, want to give an overview of, high-level overview of what it looks like on ARM, how DRTM maps on ARM, and kind of where we are with the spec and implementation in ARM firmware. And then a few kind of discussion points around how it would integrate with Linux. So yeah, that's it.
All right. And then, as I said, I'll be closing with going into some detail about the Linux secure launch capability. Just doing some foundation discussions and then explaining why we want the patch set, what's in the patch set, as well as some upcoming features that we're going to be building into the next iteration. And then hopefully answer any questions people have.
Yeah, and after all the presentations, if you will still have time and energy, we can switch to virtual pub event, which will be not recorded, not this would be very loose, casual discussion with whatever adult beverages you prefer. And during that VPub, we probably will have like other participants for open source firmware, open source hardware community. So this would be more wider discussion about how we can move forward the security of open source firmware, open source hardware, as well as whatever came. Like sometimes we're talking about security of mobile phones and what are the mobile phones of modern mobile phones capabilities, and also I think we may discuss some modern processor stuff, all the low-level things that people will bring are good for VPub. So yeah, so that's the plan for today. And just to say a little bit about VPub, like last time it took 12 hours. Like I'm pretty sure this time this would not be 12 hours because it would be 9 a.m. next day. So I don't believe we will survive so long, although maybe there will be some brave people. But anyway, feel free invited to VPub after the Linux Secure Launch presentations.
Thanks, Peter. So I guess we've still got a couple more minutes to kill. Does anybody have anything just introductory they like to ask before we get started?
I guess maybe one question I have is for getting TrenchBoot working on x86 hardware. So I mean, if I have a Lenovo desktop sitting around that supports TXT, I mean, what are the chances I can get that to work? I mean, I guess is it fairly easy, or is there specific systems that you have to use, or I mean, what's the story as far as just how easy it is to enable a TrenchBoot on a random x86 platform that supports DRTM?
So there's two different stories depending on whether you're wanting to use Intel or AMD. If you're on an Intel platform, you need to have a vPro device that actually has the Intel TXT capability available on it. In terms of ease of getting started with it, we're not quite there. I mean, it's close. We've got a set of patches that are in Grub that they're getting ready to get upstream. We have the Linux kernel patch set that we're trying to get merged upstream. Once those pieces are actually in place, it's as simple as just having them installed, having Grub installed with the secure launch capability built into it, and having your Linux kernel have the secure launch capability turned on. At that point, it's just a minor deviation in your Grub configuration than you're normally used to. There's a slaunch directive you have to add to your configuration. But outside of that, the rest of your Grub configuration is the same as the standard Linux configuration for Grub. The same thing will be happening with AMD as well. As we're trying to keep the approach as common as possible for AMD, which is where Piotr's group team has been really focused on the last couple of years. It's much more available. There are some hiccups that have been found with AMD's VTPM implementation in their PSP that Piotr and his team could kind of discuss if that's interested.
This is FTPM, yeah, FTPM stuff for some platforms coming with mobile profile, which is not capable of entering locality 4. But for the laptops, it should be. I don't know, like if they have any signs of laptops that can correctly enter the called SKInit and cooperate with TPM. That's a very good question. And we didn't try it modern laptops. We just tried. What we tried is, I believe Michał will have a table what precisely was tested at the end of the presentation. But I believe like there is a way to simplify things by providing, for example, that packages which already has built-in grapple, built-in kernel that we can just install on regular Debian and make things work. Of course, this have to be tested with certain microarchitectures in case of Intel or in case of AMD. So let's move that discussion after the presentation.
Yep, it's 11:15. If you want to go ahead and start, Piotr, with your, or no, I'm sorry, Michał is first. I'm sorry.
Could you unlock the screen sharing? Daniel?
Yes, one moment. Come on. All right, there you go.
Okay, thank you. It's this one. Yeah. Okay. Everybody see the slides?
Yes, you should be good.
Okay. So hello everybody on the first presentation of Linux Secure Launch TrenchBoot Summit 2021. My name is Michał Żegowski, and I'm a firmware engineer at Embedded Systems Consulting. I'm a core boot core developer maintaining Braswell SoC, PC Engines, and Protectly platforms. I'm also Open Power System Software Workgroup Chair and the Open Power Foundation Workgroups. I'm developing open source firmware for over 4 years, and I'm mainly interested in advanced hardware and firmware security features, trusted computing, and related stuff. And who we are exactly. So FreeMDEP is a Poland-based company. We are licensed core boot service providers since 2016, and we participate in the leadership meetings. We are also UEFI adopters since 2018 and the Yocto participants and the new embedded Linux experts since 2019. We also provide consulting services for Linux Foundation FWPDL VFS project. And also some time ago, we became the IBM Open Power Foundation members. Okay, so as for my presentation, I will try to show you how TrenchBoot works for AMD and Intel platforms. We'll try to describe some differences between SRTM and DRTM briefly, and try also to show some demos on ASUS KGP D16 or the Optiplex 1910. And at the end, I will compare how those two technologies work, what are their pros and cons, and do some summary. Okay, so to start with, what is SRTM and DRTM? Well, imagine the size of the rock you see on these pictures is actually the trusted computing base. So trusted computing base is the amount of code or data needed to be be trusted or attested to establish the root of trust. When we have the static root of trust for measurement, which is the root of trust in BIOS, it needs to set up the root of trust very early in the reset vector or pre-reset vector environment. And then you start to pushing this giant rock from the foot on the mountain up to the peak. By the peak, we should probably understand the operating system where finally all those measurements done by the BIOS can be finally utilized to perform some attestation. And SRTM has this disadvantage that it cannot the measurements are taken throughout very long time of platform operation, since the reset vector up to the operating system. And if something falls apart, then our Sisyphus may fall with the rock, and we will not have any gains from that. And of course, the higher we push this rock, the bigger it becomes, and it's harder to push it further. When we have DRTM, we can imagine this is as just a small rock which can dynamically establish root of trust, because we root the trust in a single CPU instruction or kind of piece of software that is very small and probably signed, like in case of Intel, or is just loaded by the CPU through a secure way, and it uses a mechanism to measure the software we need. So comparing those two rocks, DRTM looks much more lightweight and is very easy. Moreover, when we want to reestablish the trust, we don't have to start to pushing the rock from the foot of the mountain. We may just like throw this rock out and pick another one, and we can go whenever we want with it, for example, inside a pocket. Okay, so let's start with DRTM for AMD. DRTM for AMD is implemented with a set of secure virtual machine instructions. The instruction that initializes the root of trust is called skinit, which takes a 64 kilobyte long secure loader block and loads it, and the address of this secure loader block must be loaded in the EAX architectural register. And then this instruction takes this secure loader block to initialize the dynamic launch event. Everything is pretty well documented in the AMD architecture program manual, except some bits to disable the secure loader block protection on Zen and newer CPUs. Okay, so let's have a look at a typical boot flow of DRTM on AMD. So when we launch our platform, we typically start in BIOS, which does the platform initialization. Fortunately, BIOS doesn't need to initialize any SK init stuff in the BIOS. And we can, for example, boot to the grub bootloader when we have our TrenchBoot S-Launch module, which is responsible for preparing the CPUs and TPM for calling the SK init. And then we can load the TrenchBoot Secure Kernel Loader. Secure Kernel Loader is the TrenchBoot open implementation of the AMD Secure Loader block. And it is responsible to measure the software that we want to launch, in our case, Linux kernel. And for our advantage, we have control over this secure loader block. So we have freedom to choose what protocol we will use to boot the final software, whether it is Linux kernel or a Zen image or whatever any other software we want to launch. And SKInit instruction is available on every AMD processor since its introduction. So there's no need for some high-end CPUs or server CPUs, as in case of Intel. The only caveat with AMD SKInit is that it requires a discrete LPC TPM in order to work properly. As Piotr already mentioned earlier, firmware TPMs, which are implemented inside platform security processor in AMD CPUs, does not provide enough functionality to perform a DRTM launch, because those TPMs are restricted only to locality 0 and limited command response buffer interface. And as an example, I would like to present you a SSKGP D16 board, which is a dual AMD G34 socket server workstation from ASUS, which was released in 2010. It is a Respect Your Freedom certified hardware. Respect Your Freedom is a Free Software Foundation certification, and it has open source firmware implementation in coreboot and libreboot. And we decided to use this platform because it is good and quite cheap hardware to test TrenchBoot, secure kernel loader on the server platform. And furthermore, its open source implementation is really fully open. So we do not have any blobs, no microcode needed and other stuff, just pure source code that is able to launch the platform. But as for the KGP D16, it is currently dropped from the coreboot master branch. However, thanks to Immunify, the platform is undergoing the revival process. FreeMDEP is re-implementing the board support into the newest coreboot branch and will manage the benign releases under the short trademark, which will be providing validated and signed binary deliverables that may be used out of the box by the end users. And on the picture, you can see DRTM PCRs 17 and 18 that are extended. And these are taken from another AMD platform called PC Engine's APU2. Okay, what are other advantages actually of using open source firmware? So at the time of a platform release, the ASUS KGP release, only TPM 1.2 was supported. But with open source firmware, we can make the TPM 2.0 work, because LPC TPMs are compatible from the SKInit perspective. They just send the SKInit instruction sends the same commands to the TPM, and those commands are actually backward compatible with TPM 2.0. And I'm specifically talking about the commands that are used to open the locality 4 and perform the measurements of the secure loader block. And of course, we would always prefer to use TPM 2.0 rather than TPM 1.2 because of the SHA-1 weaknesses. Everything cool, but I wasn't able to prepare a demo of launching TrenchBoot on this platform. It occurred that the platform support code in the latest coreboot 14.11 branch, where the platform support code still lives, had issues with TPM cycles decoding. Something was probably not properly initialized to pass through the TPM cycles down to the soap bridge and back to the CPU from soap bridge. Hopefully we can fix that with the Sharo firmware. But for those who are interested in seeing some AMD DRTM example, I have pasted here some recording of SKInit running on PC Engine's APU2. Okay, let's move to Intel. So Intel DRTM technology is also called Intel Trusted Execution Technology, in short TXT. It is implemented with a set of SMX, safer mode extensions instructions, called getsec. Getsec is a set of instructions actually, because it uses different functions depending on what values are passed through the architectural registers. Getsec subfunctions that actually are used to initialize the TXT and set up the root of trust use authenticated code modules, in short ACMs, which are binary blobs signed by Intel to initialize the TXT and DRTM. The initial core boot implementation of Intel TXT was done by a 9 Elements company and was tested on OCP Wedge 100S and Facebook Watson servers. And of course, basic explanation of getset instructions may be also found in the Intel Software Developer Manual. Okay, now let's have a look how the typical boot flow of BIOS and dynamic launch looks like. So we typically start in the reset vector, as I said earlier. And in the case of Intel TXT boot flow, the BIOS must check whether the CPU and chipset are TXT capable. This can be done in only one way, actually. CPU has its own CPU ID instructions that may report SMX capability. And then, if the SMX capability is present, the CPU may invoke getsec subfunction capabilities to check whether the chipset is also capable. Only if those both requirements are satisfied, we can say that the whole platform is TXT capable and we should follow the TXT boot flow. If not, we may just proceed with further BIOS tasks, for example, to train the RAM memory. However, if we want to initialize the TXT, we have to check first whether there are any secrets in the memory left, or if there was a TXT wake error. If yes, we have to perform a special action, which is running the BIOS ACM subfunction sclean. Now, you may wonder why I call the ACM BIOS ACM, because there are actually two types of ACMs. There are BIOS ACM, which is responsible for initializing the TXT inside the BIOS. And there is a SINIT ACM, which is used by the bootloader or operating system to actually invoke the dynamic launch event to measure the software. So the BIOS ACM is not distributable. And SINIT ACM can be downloaded from Intel, but needs a click through EULA to download. Okay, so going back to our sclean operation. So sclean is responsible for clearing those secrets in memory. So it wipes the memory for us in order to get rid of those secrets and reinitializes TXT into a fresh state. And after sclean is successed, we go back to the reset vector because the platform state after sclean is undefined. We have to reset the platform, and then again we check whether the CPU and chipset is TXT capable, and now those secrets in memory shouldn't be present. So then we must proceed with unlocking the RAM controller, because TXT locks the RAM controller where there are secrets in there. If we unlock the RAM controller, then we can proceed with training the RAM and move to the RAM firmware phase. Okay, so the RAM firmware phase initializes various devices, but in the aspect of CPU and chipset TXT capability, the CPU initialization is the most important for us. So we have to ensure that all CPUs are equally initialized. So that means we have to set the same capabilities to the registers, like memory type range registers must be correctly programmed. We have to enable or get sec center capabilities in machine-specific registers, etc., etc. And of course, we again check whether the CPU and chipset are TXT capable. If yes, we initialize the TXT environment. By initializing the TXT environment, we have to check whether the BIOS ACM is present, whether it is correctly aligned, whether we have enabled all TXT functions, and whether we have put the secondary CPUs to sleep. Then, if all those checks have passed, we have to run the BIOS ACM again, but this time we select thescheck function. scheck will finally initialize TXT and log the TXT configuration so that it will be prepared for SNIT ACM to take over when we boot the bootloader. Finally, when scheck was successful, we prepare some information for the bootloader or operating system to consume. It is a special space called TXT heap, where we put various information about the BIOS, the platform, and ACMs. Then, if everything was done correctly, we can finally boot to the grab bootloader, which will further take over and initiate the dynamic launch. Okay, so as you can see, firmware requires a lot of preparation to execute an ACM via getsec instructions. And this is not over, actually, because grab will have to do almost the same job as firmware did. So it has to correctly set up memory type range registers, clear machine check error registers, and of course ensure that CPUs are sleeping. Then it parses the TXT heap structures that we were filling in BIOS, extracts the platform information, and possibly extracts the SNIT ACM from there. If not found, it may also supply, we may also supply the SNIT, for example, from the hard disk. And then when we are finally prepared to launch the ACM, we run the SNIT ACM with the getsec center subfunction. It will call into the ACM entry point, which will measure the target software for us. Since the ACM is a closed source blob, there is not much control how SNIT executes, and we do not have this freedom to for example, select boot protocols. Okay, so I would like to sorry, I would like to show you an example of Intel TXT running on a Dell Optiplex 9010. It is a nice workstation with 3rd generation intercall processors and Intel Q77 chipset. Both the CPU and TXT are TXT capable. I have a i7 processor, so I think I have the most powerful one to test with. And this is a workstation we mostly use in FreeMDEP Office. And furthermore, it also has support with coreboot open source firmware, which FreeMDEP ported. And what I will show you is how I managed to launch the TXT with coreboot. FreeMDEP would also like to provide coreboot-based Osharo firmware for this machine, and we plan to release a validated and signed binary for end users soon. And of course, this binary will be covered with FreeMDEP support. Why exactly this model of the machine? Well, third generation processors also have fully open silicon initialization core boot, except that we have to still include the microcode binary in order to properly initialize the CPU. And unfortunately, we are also bound to TPM 1.2 because ACMs do not support TPM 2.2. By ACMs do not support TPM2, I mean those exact as ACMs for third generation processors. Of course, newer processors have newer ACMs, and those probably support TPM 2.0, but I have no idea whether it is fourth generation or later. And on the pictures, you can see that I'm running a core boot firmware, and on the left there is a set of PCRs, and on the end we see PCR 17, 18, and 19, which were extended. However, those PCRs were extended using TrenchBoot, which is a reference implementation of the measured launch environment for Intel TXT. Okay, now I'll move to the demo of Intel TXT and TrenchBoot. So I'm launching the platform now. However, there is a need to initialize the environmental controller first, so I need to have a reset back there. And now we are going through the TXT initialization and booting CBIOS, which will then boot the grab from the disk. I had a Cubes installation here with anti-evenmate setup. So the tboot kicks in, performs the senter function, and hands off the control to the kernel. Okay. I also wanted to prepare a TrenchBoot demo. However, it occurred that the current grab implementation of TrenchBoot S-Launch module does not support TP1 1.2 path for Intel TXT yet, so automatically I wasn't able to perform the secure launch using TrenchBoot, despite I have the right BIOS support. But I will also show you how to perform an easy integration of core boot firmware and for Intel TXT. So in order to correctly configure core boot for Intel TXT, you have to perform a few steps. Assuming that you have already configured core boot for your target platform, which is TXT capable, in my case it is the Optiplex, you have to ensure that the trusted platform module is enabled. Optionally, you may also enable measured boot. Then you select the Intel TXT support, and you have to pass the ACM paths in order to core boot build system to include them in the image. I also pass an optional SUnit ACM, since it will be already put into the TXT heap, and grab will have the possibility to use the ACM I provide from the BIOS instead of searching the hard disk. Optionally, also, I have enabled verbose logging in order to have some verbose information from Intel TXT driver, what it does, whether there are any errors, etc. Optionally, you may also enable some higher debug level in order to see what happens and in order to not miss any information. Now, we can save the configuration and simply proceed with building the image. Okay, so as now we know how to configure coreboot for Intel TXT, we will perform some short comparison of DRTM on Intel and AMD processors. So in terms of blobs, AMD does not require any blobs, actually. We have open source implementation for that. However, we are currently supporting only Linux and multi-boot protocols with the secure kernel loader in TrenchBoot. We are not launching Windows for probably obvious reasons. We don't have any way to hook into Windows bootloader. For contrary, Intel has its BIOS and SINIT ACMs, which are required to initialize the Intel TXT. And as I said earlier, the former requires NDA to obtain and integrate into BIOS. And of course is not distributable. And SINIT ACM can be downloaded from Intel side, but the distribution is under click-through end user license agreement. In AMD, BIOS doesn't need any DRTM initialization. SKNet instruction is just there, actually. The only thing is to set up the right CPU state before calling SKNet and properly prepare TPM by relinquishing localities. Intel, on the other hand, has very, very complex BIOS initialization of the Intel TXT, which makes it very, very hard to implement the support for BIOS, like 9LMS did, for example, in coreboot. AMD may use any TPM family, actually. As I said, those commands that are sent to the TPM are backwards compatible with 1.2 family if we use 2.0 TPM. But in case of Intel, of course, TPM family support is dependent on the ACMs. So if you have a newer microarchitecture, then you are more likely to support TPM 2.0. And the last, in terms of availability of DRTM technology, AMD is the leader here because SKNet is available on all processors since the introduction of SVM, while Intel TXT is available only on the high-end i5 or i7 and higher CPUs and most Xeon CPUs. And as a small wish list, we would very, very appreciate some reproducible binary builds of all signed Intel signed ICMs with some read-only source code available outside Intel. It will allow us to verify the correctness of the implementations of those ACMs. And at last, our test matrix of TrenchBoot tested hardware. The team responsible for Intel implementation of TrenchBoot have been testing our solution on Tiger-like client devices, as well as Skylake and Kaby Lake servers utilizing TPM 2.0 and UEFI firmware. So the FrameDev team responsible for AMD part have been testing PC Engine's APU2 platform series, which is AMD Family 16 model 3030F embedded series processors, released around 2015, if I recall correctly. And we have been testing with both TPM 2.0 and TPM 1.2. And we have been testing it with coreboot firmware using CBIOS, so legacy boot. We also tried the ASUS KGP D16, but we failed due to the coreboot firmware TPM issue with the TPM cycles decoding. And we have also tested the Supermicro M11 board, which is a a compact server board with AMD EPYC 3000 Snowy Owl codename server platform. And this platform had a TPM 2.0 connected to the LPC header. And we have successfully launched TrenchBoot with legacy boot. However, UEFI boot is still not working. And today's result of the Optiplex is also a fail due to missing implementation of TPM 1.2 flow in the grub as launch module. And a short summary of my presentation is that DRTM simplifies establishing of the root of trust for measurement and is orders of magnitude less complex than SRTM. Well, at least on AMD, because the TXT serialization is quite complex still. TrenchBoot allows to integrate DRTM securely launch to any Intel machine with TPM 2.0 currently, since TPM 1.2 is not yet implemented, and the proper BIOS support, and any AMD machine with discrete TPM, because AMD FTPM is known not to work due to the lack of sufficient localities. Also, I haven't written it here, but UEFI boot is not yet thoroughly tested, and we will probably look into it also in the future. And yes, TPM 1.2 support for the grub S-Launch module for Intel TXT is still underway. And the most obvious reasons to use TrenchBoot and DRTM, because it's an ideal solution when you do not trust the BIOS. Since most of the platforms today come with some proprietary closed source firmware from independent BIOS vendors, we don't know how many bugs or backdoors are there. Maybe not backdoors, but you don't know what lies under the hood and what kind of SMM code there is. As I say, DRTM may be troublesome in the UEFI environments. For example, due to the presence of the runtime services and the bloated system management mode, although it can be, of course, containerized to restrict the SMM privileges. For example, using Intel SMI transfer monitor or AMD SMM supervisor, or however it is called. Okay, that will be everything from my side. Thank you for listening, and I'm open to questions.
Thank you, Michał. That was great.
I was scared for a little because the window of Zoom disappeared, and I thought I was talking to myself all the time.
No,
Okay.
no. That's everything was on YouTube.
Wow.
So, anyone on the call has some questions?
One question or point on the on one of your tables, you said that the AMD system has no blobs in it. And you said that there's no microcode required. And whilst that is technically true, you do not want to be on the embedded microcode on those processors. You really, really do want to take the latest microcode update, because that's the one that has the Spectre v2 fixes in it on that CPU. Yes, your operating system does not want to be running without that microcode.
Yeah, but this particular platform is, and this processor actually used on this platform, is the one of the last which still works with the embedded microcode. The one generation later already had problems with the embedded microcode, so it is required, for example, to update the microcode in order for example, the IMU to work properly or virtualization stuff. So yes, you're definitely right, but with the special model of CPU, it is possible to run on embedded microcode without issues.
Yeah, Michał, there are some questions about if you can drop PDF to the matrix channel of VPUB. There are some people asking for PDF. But yeah, you can free to do that after the presentation. Yeah, so you said that some things are repeated in bootloader by Grab. Why this happen?
Some things are repeated. I'm hearing correctly?
Yeah, repeated, like you said, that bootloader repeats some work already done by firmware, I believe.
Yeah, I just use this kind of statement because most of the things have to be done similarly before launching the ACM. Like it is a prerequisite in order to launch ACM to clear machine check registers, prepare MTRR registers, and ensure that the SMX is enabled or center functions are enabled and all secondary CPUs are sleeping. So it's a must before launching ACM, like in any situation.
Yeah, I would say like for future presentations, it would be great to have like, I don't know, comparison of the stacks which are available, or comparison of the set of stacks on which TrenchBoot can work. Because that last table was great, but I believe we can improve it to show precisely what software stack was used there, what operating system were tested in given case, and so on and so on. And about closed source nature of ACMs, I believe everyone see that right now probably this would be open source, even if there will be no support for TPM 2.0. There will be open source consulting companies like 3MDEP, which will probably either get grant or customer or did it ourselves to enable that support. So if anyone will do, like ARM will do future DRTM development, definitely like if it could be as open as possible so people can extend, I don't know if there will be TPM 2.1 or 3.0 in 10 years. So we can, we would not be locked in with some weird binary blob with closed source, SciNet, something which is not extensible, like with Intel right now.
I have the question regarding the AMD implementation of the DRTM. I am familiar with the Intel one, but that's some question from the to the AMD side. So, for example, at Intel, a CNIT is signed by the Intel SKI, and when you are trying to launch a CNIT using a Etcetera Center, Inter CPU, the microcode is validating the signature of the CNIT using the embedded Intel SKI inside the microcode.
Yes.
So if AMD does not provide a blob and a CNIT blob, and for example, you can create that one. How the CPU microcode verify if the CNIT is trusted and it's not somehow malformed from by the attacker.
Okay, so the thing is, there is no verification of the secure loader block, which is an equivalent of the SNIT ACM here.
Well, there's no authentication of it. It is measured into the TPM.
Yeah.
So anyone who can access the TPM later can check that they were loaded by the correct binary.
So the microcode is measuring that's right.
The SKInit instruction streams the entire contents of the block into the TPM, into PCR 17. I think it's PCR 17.
Yes,
yes.
Yeah, there's two different security models going on here, right? You have one where you have Intel is authenticating through a signature verification of your configuration component to your launch, right? Whereas with AMD, they are leaving it to the attestation to verify that the right configuration block was loaded. In both cases, the configuration environment both the ACM and the secure loader block for AMD are measured by the CPU, as Andy was highlighting. So you still get that measurement in PCR 17 for both of them. Intel just goes to this extra step of how an initialized authentication before they allow the blob to load in. And there's a couple of reasons for that, because it's not just about measuring or what you're trusting to measure the chain. In the case of Intel, the ACM has a lot of power, a lot of control over the CPU, that it can manipulate things when it loads. So you're trading off, pros and cons for what you achieve with those two different approaches. So basically you get two different security models, but at the end of the day, from a DRTM perspective, we're more concerned about what was the measurement what's the first measurement, and was it what we wanted to be there?
Yeah, that approach sounds okay.
Okay, I believe we got 6 p.m. in Central Europe time, so we should switch to next presentation.
Yep.
And definitely we can continue these topics, because I believe, Łukasz, there is a lot more to the question that you asked. Do you see my screen?
Yeah.
Yeah, go ahead.
Okay. Hello and welcome to my TrenchBoot Summit 2021 presentation. It would be about FobName, the attestation token in your pocket. My name is Piotr Król. I'm 3M founder. I'm open source firmware and open source hardware promoter interested in integrating trusted computing technology, conference speaker, organizer, co-organizer. I'm 13 years in business, 7 years in open source firmware and trusted computing technology integration. I'm also C-level in various organizations. That logo you can see on this slide. I will not repeat this slide. Michał already mentioned 3M is core boot license service providers, UEFI adopter, Yocto participants, and Linux Foundation, FWPD, LVFS official consultant. So first of all, thanks Michał and others for preparing this presentation. So what's FobName? FobName is first of all project that aims to create reference open source firmware and open source hardware implementation for USB tokens. So those can be enabled with user or administrator capability for determining the integrity of the system. And we hope, or we think, FobName will improve trustworthiness of integrity checks by leveraging the DRTM technology. As FobName is a essentially attestation server on USB token, which can attest dynamically launched measured environment, which is the end state after the dynamic launch event. And FobName is a project founded by NLNet Foundation. So this concept is not new. It was presented in 2007 by McCune, by the way, creator of other interesting papers like Flickr, which is one of the most interesting application of DRTM technology. On this picture, we see very simple use case of FobName from the perspective of user. So let's say we have some device and we have our FobName token, and we're just coming to this device, putting the token inside the device, and then the whole magic begins. The DRTM process is kicked inside the computing system, and then at some point, dynamically launched measured environment is running there. Whatever payload it has, it is attested with the server inside the token. And if attestation succeeds, we have green light. And if attestation fails, we have red light. This is a piece from the McCune paper. So with FobName, we plan to provide reference architecture and reference source code for the given tokens. We still at the point of talking with various early adopters to select the tokens. I will talk about this on later slides. And then this token can have feature of attesting whatever is going on inside. You can also see the website here of the project. We will put the updates there and information how to build the firmware, where to get the tokens, and what's really going inside, since this is like quite complex process that we're going through. What kind of features FobNail will have? First of all, it will be the open source implementation of the iTurtle security architecture concept presented by McCune on HotSec 2007. This is like a one piece, so very simple device, just showing green or red light. Maybe in more complex cases, we will have LCD, which will show something more, some additional information. But let's start with the basic. Second component, which is very crucial to implementation of FobNail, is attestation server, and we selected IETF remote attestation procedures, IETF RATS, which is standard for remote attestation server that IETF working on, and this reference implementation of that standard was performed by Fraunhofer Institute, and it is called reference interaction model for challenge response-based remote attestation, in short, CHARA, and you can find it on GitHub. And one of the key features will be attestation of platform integrity at early launch. So during the DRTM, we have early launch, which means like during boot process, we run whole operating system through DRTM dynamic launch event. Or later, we hope when the Linux kernel patches will be merged and a bunch of other things will pop up, like Zen DOM zero-less environments. Then we probably will have also runtime stuff, when we put the token, then a whole platform can do the dynamic launch event and attest at runtime. And we hope to add sophisticated attestation policies, so we can say, okay, there is some spectrum of trustworthiness of the stack that was attested, not only like just binary, but also some spectrum, or we can just add some more complex decisions. If this kind of software is running there, then it's okay. Or if this set of versions of given software is running there, it is okay. Otherwise, it's not. We hope to have multiple reference integrity measurements. So reference integrity measurements are kind of manifests of measurements which will be stored inside the FobNail token, and those will be used for comparing to whatever we will get from the machine. So we would like to, with one token, be able to attest multiple devices or multiple states of the device. And we can say this would be kind of offline remote attestation, because if we have server on the USB token or whatever the protocol will be in future, because it doesn't have to USB, it can be Bluetooth or whatever. We just we don't need internet connection to attest whatever is running. How the FobNail usage would look like? So first of all, we will get unprovisioned FobNail token, and we will have some platform on which we would like to perform provisioning. So most probably we would like to take ownership of given token, which will come from some vendor. Probably we would like to create our identity and encryption certificates, which we will flash and lock on the device. And then we will provide reference integrity measurements, some policies for attestation, and maybe we will have some protected objects like passwords or whatever. We will keep there some keys, so this token can provide for correctly attested environment. Then for provisioned FOBNATE token, we can perform attestation. If this attestation will succeed, we can either provide some protected objects or just simply indicate to customer that platform is either trusted with green LED or untrusted with red LED. Maybe switching topic a little bit, you may ask why we torturing the RTM so much and kind of a little bit neglecting SRTM. And Michał already said a little bit about that, but we're doing SRTM in 3M depth for quite a long time, and we have to say this is very complex. And if someone compares two technologies, SRTM is very hard to maintain, and I would like to bring some arguments for that. So first of all, SRTM, static root of trust for measurement, would be as good as the first measurement. So because this first measurement is so important, the code making it have to be somehow protected. Typically, it is done by some vendor-specific technologies, which are typically closed, either in some boot ROM, in management engine, or platform security processor, or whatever secret technology given vendor provides. So we have things like NXP high assured boot, Intel secure boot, or Intel boot guard, AMD hardware validated boot, or this kind of technologies. And those technologies protect this initial code that performing root of trust for measurement, static root of trust for measurement. To provision those technologies, we typically need NDAs and some proprietary set of tools. More to that, to establish that in correct way, to create correct policies for SRTM, we have to maintain 20 keys and certificates in secure manner, which is not easy. And this kind of method of playing is quite well established in kind of oligopolistic environment of silicon vendors and independent BIOS vendors. Of course, right now, there are also open source firmware vendors players which kind of trying to enter here, and either through reverse engineering, either through just gaining more attention from silicon vendors, are able to obtain documentation and then publish open tools for SRTM provisioning. And other problem that is with SRTM is lack of standardization around measurement reporting and around event log. Typically, establishing trust with SRTM, typically, it's always like that. It requires platform reset. So that's the difference with DRTM. We have also problem with lack of firmware supply chain transparency. So the components that coming and are measured at static root of trust for measurement path, boot path, are hard. We cannot identify where they're coming from. Are those measurements correct? What those measurements really mean? We getting things in PCRs, in TPM, but who cares if we cannot even confirm this is correct or not correct? And all those issues cause very slow adoption, complexity, and mistakes during the implementation. Of course, we see that on Black Hat and DEF CON and other conferences that companies discover more and more vulnerabilities in Intel boot guard and similar technologies. There are also some open implementations like Core Boot vBoot for Chromebooks, for PC engines, and we plan also to implement some for mentioned KGP D16. And we typically rely on SPI features through one-time programmable registers, which log piece of SPI to be read-only, and that become static code root of trust for measurement. And that protects the static code root of trust for measurement. So I don't know how good you see this picture, but on this picture, you can see that how really complex the SRTM implementation is. As I said at the beginning, we have some PSP-ME boot ROM, and then we're going into UEFI, which has multiple pieces, and those pieces contain various implementation. Either first is from silicon vendor, which typically covers the first phases of boot process. Then somehow we have to connect the word of silicon vendor with official UEFI secure boot specification, which requires some gluing that typically coming from independent BIOS vendor. And then we can continue with standard UEFI secure boot, which is in the spec. The same situation we see for Intel and AMD. In case of the DRTM, of course, we still got the same problems if we want to use SRTM, but then we have additional capabilities to establish root of trust, even in environment for which static code root of trust for measurement was not protected, or at least we have concerns about its quality or its supply chain. And from what I understand, most of the modern use cases for DRTM going in this direction. So let's say we don't really know what's going on with the firmware. So let's run the dynamic launch event, and let's make sure in what state we have, and then in that state we can update the firmware. This does not require platform reset. Depending on vendor, we can be fully open source with AMD, definitely, with IBM also, with ARM, I hope so. And for Intel, there is still way to change, I believe, in future. For open source firmware components that we deliver, still you got full transparency of supply chain, because you can check repositories where the code coming from. There is certificate of origin for the code. For TrenchBoot, the same thing. And I believe the landing zone or secure kernel loader can be so small that in longer run probably can achieve common criteria certification. The patches, as you know, are already there. Nobody mentioned iPXE, but iPXE is already there. So we believe this path is a future of attestation and making sure that the platform is in correct state. But either we're using kind of self-attestation by revealing the secret from the TPM, either we use kind of separate device or remote device for attestation, and one of these devices can be fob name. For modern open source firmware boot flow, we see very interesting direction that many modern booting processes involve kexec. So it typically run Linux inside the lowest level firmware, and then inside this Linux we kexec next system. This was proven by existence of projects like PetitBoot, which is bootloader for OpenPower, and many other cases, many other hardware platforms. There is Linux Boot, which already has system-ready certification done by ARM for servers, so that's achievement of Linux Boot. And there is Heads, which is also quite popular in some communities. And we know that kexec successfully bootstrapped Linux, Windows, VMware, FreeBSD, Zen, and probably other hypervisor kernels. And we know that kexec already got signatures verification capability, and we believe it will gain DRTM capability, so dynamically launched event capabilities. And I know this is already planned for the next version of the Linux kernel mailing list patches. So saying about that, having additional device that can attest this process, if this will happen, this will be real implementation delivered to various devices, it would be very helpful. So how this modern open source firmware boot flow look like for, we're saying here about PetitBoot, Linux Boot, Heads. So typically, let's say we have core boot here, the initial boot block is kind of self-measured, unprotected. We're starting with it, then we measure and execute further phases of the firmware. If this is core boot, then at some point we kicking some payload, which is Linux Boot, Heads, PetitBoot. And then because all the measurements taken over the boot process are correct, we can unseal if PCRs are correct, we can unseal the salt for generating hot P, which is then sent to USB crypto token, which as an external device can prove that whatever happened on the device is okay, and we can indicate that. And this is what's going on many interesting new devices using modern open source firmware boot flow. And then finally, HEADS kexecing or whatever Linux based payload kexecing operating system. So what features we got here? We're getting measured boot. We're getting kind of platform open source firmware self-attestation, because the attestation is local. TPM unseal things when everything is correct. We have some visual indicator of platform attestation on the external device, which is not related electronically to the laptop or to the computer that we attest. And we may have signed updates of firmware and OS. Then we can re-own the boot process by having verified boot or other technology for the firmware. And we also can have some update process through LVFS FWPD support. Of course, there is no DRTM in all this process. This is purely measured boot open source firmware with kexecing at some point, plus external device, which is our USB crypto token to do visual representation of self-attestation of the device. But what are the problems with this setup? First of all, boot block is not protected, so there is no root of trust. So we have no write protection or any boot guard that protects this initial code. So there is potential firmware replacement attack. So the token that finally present the state really present platform self-attestation result, which can be kind of faked because of lack of this initial security components. Even on the OS research website, we got note that if an attacker can control the shared secret, which is then revealed by TPM, so this can be controlled by directly sending PCR values to TPM. So that means if we replace firmware, we can do that. The attacker can install malicious firmware in the SPI flash and generate valid hotp codes. So that's kind of problem that authors knew. And this is what exactly happened in this attack scenario. We replace the firmware, then PCR measurements are faked and replayed to TPM, and then TPM thinks that everything is fine. We unseal the secret, which is then in some combination sent to the USB crypto to present the state. And of course, we got problem because USB crypto token, which is external, saying that everything is fine, and it's not. How things will look like with fobnail or crypto token that has fobnail features. So in that case, we still have exactly the same situation, that there is no additional protection, but our USB crypto token performed the attestation based on some policies, and this unsealing still have to perform exactly the same thing, but the kexec happened through the RTM event, and at some point we realized that the executed system is not exactly correct. So as you can see, we still getting the situation in which TPM quote that USB crypto token received is faked, but then we unseal the secret if this quote matches, and then during the kexec process we execute the RTM event which extend PCR 17 with correct measurement of our operating system. and then we make sure that the operating system is correct because the DRTM event measured that. And what we can see here is that despite core firmware before was compromised, we getting correct measurements in PCR 17 to 22 in the DRTM PCRs. And those PCRs then can be attested with the USB crypto token. And in that case, despite first stage was shown incorrectly that the state is trusted, the further phase of booting operating system will show that everything is correct because we were protected by the DRTM. So what kind of other use cases we can get with FobNail? So first of all, we can protect ourselves with this scenario, but we can also generate way more other scenarios. So first, we show here end user scenario, but definitely there are more use cases. We can use the situation in UEFI-based hardware environment and kind of ignore whatever is inside UEFI in firmware that has unknown supply chain. And thanks to the DRTM, we can just attest whatever is after dynamically launched event. This feature seems to be very interesting to companies that producing network appliance for runtime attestation. So we can imagine a situation in which we have some network appliance which running very long in server room. And to be honest, we have no idea what's going on in the memory at that point. And there are projects like Linux Runtime Guard, which could be run as a dynamically launched DRTM payload and check platform if everything in memory is okay and if there are no exploits in the memory or some other threats there. We can also do network booting through iPXE and do the attestation. So that means platform have to attest itself before it even can fetch some images, or it can attest locally to FobNail if everything is okay in establishing trust relation between remote network device and our network endpoint that we want to provision over the iPXE. We can do hypervisor early launch or even late launch if we will have DOM zero-less Zen, for example. We can do attestation of cloud hardened VMs. So let's say we have some Google shielded VM out there and we just want to attest that with our FobNail. This could be possible. And there are even more use cases, like we can imagine that let's say cryptocurrency wallet running on our device will be run inside dynamically launched measured environment, and before signing any transaction, it will attest with the token. Or even crypto material will be available for use after the correct attestation. So who support us? So first of all, I believe Jan is on the call. So Nitroki consider becoming our early adopter of FobNail features. So we believe that if the FobNail project will be successful and we can deliver according to the agreement with Nitroki, then FobNail feature will be integrated into some tokens. Then we also discussed with other parties. We reached to Michael Eckel from Fraunhofer Institute. He said that this project is very interesting, and even in the past, he considered this kind of device. Daniel obviously support us. Thierry Laurion also is interested about FobNail and its future capability for leveraging in HEADS environment and in attestation. We also have support of scientific environment in person of Marek Zmuda, who's a cybersecurity researcher and system security architect at Intel, although this is not related with his Intel work. It's maybe more related with his IEEE membership. We also discussed with F-Secure. F-Secure is interested and would be glad to help integrate FobNail features in Tamago firmware. So yeah, so definitely there are already parties that are interested in working with us in enabling FOBNAIL features. What about the hardware and software stack? We're still at early stage of selecting what we will use. Initially, we selected that this would be Nordic NRF 52840. And yeah, so in longer run, we can consider even some RISC-V FPGAs or whatever will come from European Processor Initiative. And in case of firmware stack, we want to use Rust, although we probably will have to use C bindings for Chara, since Chara is in C right now. Maybe in longer run, it can have a library in Rust. Definitely HAL for NRF already exists. There is a very interesting crypto library called Tracet, which is already in Rust. So this is something that we will leverage. Yeah, and what about the status of the project? We have multiple phases. Right now, we finished phase 1, which is implementation of the built infrastructure. So we already got containers for building Rust firmware for NRF 52840 USB dongle. This is public, so you can go to FOBNAIL website and FOBNAIL repositories and reproduce the results. The second stage is communication between attester and FOBNAIL token. So right now, the attester will be just like in the platform. It would be not yet run in dynamically launched environment, but we have to start somewhere. At this point, we will make sure that the communication method that will work for Chara and the platform will be established. To do that, we will expose USB device, network USB device to the operating system, and that would be the main task. And in that way, there will be not network connectivity going through over USB device. Thanks to that, we can not change Chara and just use normal, like regular network server, but inside the phone. Phase 3 would be local platform provisioning development. So we would like to have all the processes of generating the keys, provisioning the platform, tying this to the given owner, and so on, like mapping, getting the reference integrity measurements, dropping this into the token. In phase 4, the FOBNAIL token provisioning development, we would like to make sure that multiple platforms could be supported and that we can perform attestation of that. Then finally, we will check the attestation, test the attestation between various platforms and really make it work correctly. Then the FOBNAIL token service will run the attestation after the device is plugged. So this is like detecting that the token is connected to the device, and we trigger some either we will use UDEV, either for our own open source firmware implementation, we can use SMI. There are various ways of doing that. And finally, we would like to create a research paper to spread the word about the implementation, to explain in details how this is implemented. Then we have to move everything into some RTOS or even bare metal implementation in dynamically launched measured environment. We hope to have very minimal library, most probably written in Rust, so anyone can create new dynamically launched measured environments, or DRTM payloads, as we call it, to use on the other side of attestation process. And finally, there will be development of the boot time measurement verification, and during that we would like to communicate state to that FOBNAIL token, and finally decide and display either red light or maybe some more sophisticated message, what's the state of the platform. Yeah, and that would be it. I believe I'm over time for this presentation. Yeah, 3 minutes after. So any questions?
You actually had till 17:45.
Ah, okay.
So you still got some time. Got about 10 minutes for questions.
Okay.
The PO
Any questions? Yeah.
What are the hardware capabilities of the microcontroller that you're using?
So this is the same microcontroller used by OpenSK, a Google project. So it's like, I would say it's quite good. If you're asking me about precise algorithms, I would not say from top of my head. I know that AS256 definitely is supported. Hamax SHA-256. Yeah, so it's like very easy to check in the Nordic data sheet. I believe this is FIPS certified device, so some minimal set of like random number generator and various features have to be there since it's got the certification. So let's. I just found this. If I can drop that to the. And to be honest, I'm not sure if at this point we are like, of course, in long run for production devices, yes, this is very important. But right now we are more concerned about putting Chara into the token, enabling communication channel with the DRTM payload. Those are like things that are concerning us. And like, for example, exposing Ethernet device after connecting to various operating systems, or like first would be Linux, but in longer run, we would make sure this is compatible with other solution. That's something that is concerning at this point for us. But what precisely are you looking for? Like, what precisely is concerning you in terms of cryptographic capabilities? I'm not sure who asked the question, but.
Okay. Well, so a question I would say is, maybe I missed it on the slides, but you have your phases. Do you have a timeline on when you'll be getting to the various phases of the project?
Unfortunately not. So the idea was to go through all the phases in 12 months, but we're a little bit delayed. One thing because of the initial papers, because of kickoff of the project, and then like this is like not small project, and I believe we may face some obstacles that we didn't predict it yet. We already see like right now the selection of correct Ethernet device model and like finding correct implementation, how much it will take. It's hard to at this point judge because we didn't do like extremely precise analysis and research at the beginning. It's like at the beginning it was most concept, but feasibility of that is there definitely. But rather the question is, do we have to write the libraries ourselves? Do we have to develop this driver ourselves? Maybe there's something ready to use, and that's more what we're doing right now. And to be honest, it's very hard to say. I don't know, like I will target middle of the next year or something like that.
Well, obviously I'm very excited, so.
Yeah, I believe so. So definitely the most important thing would be payloads. And yeah, I don't know what payloads we may have and how far we can go with those, and maybe what are the already existing commercial payloads with which we could somehow communicate. Maybe the protocol, the Chara protocol, could be integrated in those, and in that way we can also leverage various existing applications. and those do not have to attest to the cloud or attest to some external server, but attest locally. I don't know. That would be very cool. And yes, we still didn't have enough time to explore that environment. I believe that's probably the most exciting part, if we would be able to convince some players to do that. And from for example, ARM perspective, that could also be interesting thing to like have some, let's say, demo reference payload that can do that thing, do the attestation with Fobnail using Chara protocol.
What about using NFSC instead of USB?
I don't know what limitation we may have over NFSC in comparison. There was one person, I don't know if he's on the call, but there were questions about using Bluetooth. So I don't say, if like if we will use probably IP communication over whatever. With NFC, I don't know, like that means we don't have that layer. So the question is, like then that would mean we have to somehow convert things and apply to different layer, different communication layer, which probably implies, size of packets and so on, which
right.
can be problematic at the beginning. But I don't know, maybe there is a way of integrating IP communication over NFC or in some simple way transport, because I don't know if we would like to change the protocol.
Yeah. Okay.
Yeah, there is something like IPv6 over NFC. There is IETF draft for that. So.
Okay. Does anybody else have some questions for Piotr?
So there were also ideas of exposing, let's say it could also work in a way that, because right now there's this problem of setting up an attestation server. Like we may ask ourselves, okay, what kind of attestation server I should use, where to get that, how to set it up. Maybe some existing attestation servers which are there are quite complex in setting up. And in that situation, if Fobnail will expose network connectivity, of course, the performance could be kind of questionable, and we will see how this will happen. But then when you connect this to some firewall, you can just provide the attestation services for all your network. Of course, assuming that it has Chara compatible protocol.
Oh, well, then you could definitely do something like a LoWAN or some other IoT network protocol that would be supported on an embedded device like that, and you could just do your attestation for your IoT network.
Yeah. So Demi asked about, could Chara be replaced with minimalist protocol run directly over USB or NFC? Yeah, that's a very good question, but I believe definitely we didn't predict that in this grant, and we will not cover that in this grant, but maybe this is good target for next grant. But first we have to prove that things work and that this is usable. And when I'm thinking about that, I'm not sure if this makes sense, because we can easily end up in creating a transport-specific protocols. Like, yeah, we can go even further. Let's say LoRa, yeah, and LoRa is very kind of problematic. So let's attestation over LoRa with very small, like, I don't know, 50 bytes packets or whatever, or 15 bytes packets. I don't know if we should go that path, because we easily can end up maintaining multiple transport dependent protocols, which is probably not very good for the project.
Yeah.
I would go IPv6 or like IPv6, and then maybe this can be used in like 6LoWPAN. All this, like IPv6 seems to be the best choice.
Right.
And ultimately, it's a trade-off between flexibility and attack surface, and the reality is that you can mitigate some of the attack surface with things written in Rust and stuff like that more easily than you can deal with problems of, well, I kind of want to run my network on, I want to do this over the network because that makes dealing with my 1,000 IoT devices easy.
Yeah, so interesting comment from Demi is that in CubesOS, for instance, DOM0, which is currently to be attested, has no internet access. And that's very cool. I wonder, like, what would be first, Fobnail or DOM0 less Zen? Who want to take the bet?
Well,
DOM0less already exists, but
yeah. Well, I think when he says DOM0less, he's referring to what we've now called hyperlaunch, which hopefully we should have patches for that starting to come out soon.
Okay, let's see, because in that way, I assume in this situation you have some admin VM. Yeah? There is no DOM0. There is just like.
All right, so we've hit the time, so this will definitely be a discussion for the VPub. Just a nice little.
Okay. Yeah.
Sure.
So let me share screen with second presentation. Okay. Hello, everyone, and welcome to my second presentation today, which would be about LVEFS host security ID and silicon-based core security, especially in context of DRTM. So, like most of you probably were here during the previous presentation. So, just shortly, I'm Piotr Król. I'm 3M founder and CEO. And I'm an open source firmware and open source hardware promoter, enthusiast, and integrator of trusted computing technologies. Also 3M Dev. We'll skip that. I would like to thank Michał Kopeć, junior firmware engineer in 3M Dev, who's main contributor to this presentation. So yeah, the goal of this presentation would be to introduce you a little bit to how host security ID is created in FWPD, and then based on that information, we can talk about how DRTM checks could be introduced into LVEFS FWPD ecosystem, because we believe this is important goal to achieve. So everyone can check if the platform either is capable, either already maybe working with DRTM and maybe working fine or working not so fine. So what's the problem? Why even this host security ID pop up? So the problem is that there is no easy way to determine level of platform security, and in a way that is that could be understood by end users, not only by security professionals who whole life sitting and analyzing hardware and software. So for now, like what we can do today to evaluate the level of security of given platform, we getting NDA documentation, we trying to get source code of everything what's running on the platform, or maybe we getting the skills of reverse engineering the code which is running on the platform. Probably we need some deep technical knowledge of the hardware, firmware, bootloader, hypervisor, OS, 10 system software. And maybe we even consider some new frameworks which can evaluate security of our systems. There are many frameworks that popping up recently, and all of that is of course like very problematic, and it's too much. That's why we need something simpler. The project released by Intel security team, we call it ChipSec. Back in the days, it's already like quite long. This project was first one could try it to address the problem. It was quite successful to some extent, because this was first project that show that, you know, running some simple Python stuff, you can evaluate, okay, what's the status of secure boot? Is it enabled, disabled? Maybe maybe it is the SPI is correctly protected or not. Maybe your database is correct, secure boot database is correctly populated or not, and so on and so on. But it required sometimes tricks. Sometimes for some checks you needed to disable secure boot, and sometimes you needed to load unsigned kernel modules, which is maybe not for you. And because of that, this was problematic for regular users, and we needed something simpler. On the other side, chipsec was always very Intel-centric, and there was no AMD checks in it. At some point, 3MDev wanted to contribute something, but we didn't found time on or sponsorship for that work. Not all modules. We know that chipsec is project use it in various places, and some modules are not open. People just keeping stuff for themselves. And I'm not saying this is a bad thing, but definitely it could be bigger and better ecosystem if contribution will be kind of more bigger and driven by bigger community. And we're going into era of FWPD and LVFS. So what's FWPD, LVFS for those who don't know? This is a Linux Foundation project maintained by Richard Hughes from Red Hat. The project is written in C with LGPL v2.1 license. Its initial release was in 2015, and it essentially contain two projects, we can say, but those work in tandem. There is FWPD firmware update application, which is running in your Linux. I believe they can even support other operating systems. Although I didn't go deep into that. We did FreeBSD support for FWPD. So yeah, definitely it is possible. And there is other part of that equation, LVFS, which is web service, which provide host updates, plus got some nice web interface for managing roles in uploading the firmware, in checking the status, how many firmware were downloaded, and what was the update success rate, and this kind of stuff. This project grew over the years as right now probably the biggest database of firmware updates. Through Linux Foundation, they were able to reach very important major independent BIOS vendors, OEMs, ODMs, and thanks to that, there are many prominent top OEM names on the main side of the project, and that makes it a healthy, good project and good target for goals that I plan to present in this in further slides. And they already proved that they are capable of enforcing some policies regarding firmware update quality. So, for example, discussion about release notes, quality, because like many firmware updates contain in release notes something like updated improved performance or fixed ticket 1, 2, 3, 4, which is like not very descriptive and not very helpful for anyone. And plus, thanks to that, they were also able to grade the firmware updates based on some detected features or some reported stuff like PCR zero measurement, which is important. And then in version 1.5.0, FWPD introduced host security ID, which you can see on the screen. So this is like a subcommand which gives some report over things related to the security of the platform, including firmware, including maybe something in OS, maybe something related with configuration. And this, of course, was possible thanks to vast information that FWPD already possessed about these binaries and about the quality of them. This led to creation of HSI specification, which was published and signed by Richard, Mario, and both Alex Bazeniuk and Alex Matrosov, which are very well-known names in firmware security environment. And the essential goal of the specification was to provide easy-to-understand information to people buying hardware, and probably not only, because I believe this also is used to justify some moves inside corporate environment and to easily check things what's going on in bigger organization with status of the firmware. The documentation is available on GitHub. You can read it. But I would like to go into the levels that the specification defined. So lower the level, lower the security, we can say. So HSI 0 is essentially insecure, means none or few firmware protection enabled. It is lowest security level, which gives almost nothing. But even if at this point we have some failures, that means it's something wrong, very wrong with the device. Then we have critical. This is most basic protection. It may be or may not be sufficient to protect against remote attacks. Those are like very generic descriptions of the levels. And this level is considered essential by security professionals. So if you want to do anything security related, this is like absolute minimum that you have to have. And failures at this level are considered critical, and system should not be used for any serious task. Then next level is risky, and this one protects already against more difficult attacks. And this security level corresponds to can address even some theoretical concerns not already exploited or not exploited publicly. Yeah, so there are various technologies employed here to detect. Then we have level 3, which is called protected, which is high security, and this is like out-of-band protection of the system firmware, and may even include some recovery of the firmware in case of some problems. I don't know, probably dual BIOS is some of that protection. Then level 4 is secure. There is assumption that there is no issue, several layers of protection for firmware existing, and for example, there can be encryption or some execution protection for system firmware. And then finally level 5, which is secure proven. This is level that there is no test for this level because the assumption is nothing. This level cannot be yet obtained, and this is just like the top of all security levels defined. Maybe let's run how you can obtain for this for your device. So this is just very simple. You just run the FWPD security command, and just like force to obtain some status. And as you can see, there are already some on the devices that we tested. There are some passes, but also some failures. So this is quite simple. If you install from your distribution, then you got that out of the box, so you can measure that very easily. But then how to add another test? How this is implemented? So below is an example of the plugin that provides some attributes. So first of all, this example could be, for example, SPI flash access information. This information is exposed in sysfs. Of course, the assumption here is that this information is correctly exposed, because all the measures that FWPD does requires no additional hardware, no additional software firmware installation. So they assume that the system itself can expose, or some properties of the system can be checked through software means. And that, as you can see, there are function, there's interface here defined with full plugin, platform integrity, ad security, attributes. And if we go further, this ad security attributes defines checking something in sysfs. In this case, this is BIOS write enable bit, BIOS lock enable bit, and SMN BIOS write protect. So those are similar checks that chipsec did in the past, but just implemented inside the FWPD daemon, which sooner or later probably will be part of every Linux distribution and on maybe even BSD systems. So when we're trying to add new test to HSE, we just like issue PR to the repo. That's normal stuff, and then we add some new criteria ID in the lib FWPD in the FWPD security at private header. We add entry in HSI documentation, so everyone can read what we understand by assigning given level, and then we implement or extend the ad security ad function, or we even create new plugin, depending on what kind of set of things we want to check. So as an example, we did the plugin that checks CPU vulnerability mitigation via sysfs. So we wanted to check if the meltdown vulnerability mitigation is enabled. We started by creating new plugin, which we based on the platform integrity plugin, which I showed before, and we just added some define, and this then we added the name of the test. So this name will be displayed on this beautiful screen with green and red marks. In this case, we call it meltdown mitigations. Then in the attributes, we checking sysfs for the existing of the file, and then we checking if given file exists, and then if it contains some content, and then we report either failure, either success. And this is how this will look like as a result. So you can see meltdown mitigation enabled, and that's how this works. So now we can move with some like what kind of other features are implemented here, but then like we can use that methodology to add DRTM checks, which is like, as you can see, quite simple. But the key point is, of course, how to select the given test. So as an example, how different features are tested here. For example, boot guard detection is read from HFSTS register. Flash protection features are read from PCI config space. Some Intel TME existence and presence is read from CPU ID. Intel ME related stuff is read through MEI interface, and we obtain firmware version. We can check flash description override status and check if the ME is in manufacturing mode or not, which is depending on the status. We may decide if this is secure state or not secure state, or what are we passing or are we failing this criteria. For AMD, there is not much. There is AMD TSME check, and which simply contains reading from MSR. Everything is still very UEFI x86 Intel-like. This is probably because of chipsec as a source of influence, but definitely there are features planned for ARM and RISC-V. Other support, like other environments or other firmware support, is like right now non-existent. CubesOS detection via Cubes FWPD, which 3MDev contributed, does not work. So first of all, like the wrapper script right now does not understand the security option. Probably this would mean some extension, but the question is if in CubesOS we need that. If we have CubesOS certification, then that's already come from with some level of security. Of course, it would be great if we can prove that even with FWPD, with another system that can judge what's the platform security level. Core boot protection, like not detected, so vboot is not detected. There is no detection for chip-based flash protection. And yeah, so it would be great to implement that and add that to FWPD. There is also heads, which provides, and any like similar environments which add protections, and this is also not supported. But there is space for growth. In case of DRTM, so first of all, the question is where it belongs to which level. It seems to belong to higher levels. I don't know if we can consider DRTM as a essential, like lowest, like HSI 0 level thing, but that's good discussion what level it should be. And then how we can really confirm that DRTM is configured correctly, is deployed correctly, can be used correctly. And definitely first we have to check like if there is vendor-specific method to establish trust. So if their instructions are supported, first probably if the virtualization is supported, because otherwise, like that's first thing. Then like how to check DMA protection. So that means IAMU configuration. One thing is that IAMU is enabled, but other things, is it configured correctly? And I don't know if we can check that from the operating system level. Maybe there are some ways. SMM protection seem to be even harder. I don't know, like there was suggestion from Christian that we should like have SMM exploit, and if it works, that means the protection is not correct. If this doesn't work, that means like everything is fine. But like shipping FWPD with SMM exploits would probably not be approved. Then TPM 1.2, 2.0, then how we can judge that, like one or the another. I don't know if we need TPM event log. Definitely is not essential, but would be helpful in judging, okay, what kind of level of security we have. Definitely good TPM event log can help in, and of course, compare it with available information about reference integrity measurement. That those two things would be very helpful and can confirm and determine platform security level. Yeah, so we can extend HSI specification to include. So I believe this would be first step to extend specification. Of course, it has to be extended with the tests that can be performed. So definitely we can do CPU ID detection and check the features. We can check TPM presence and if it is functional. Although I don't know like how much really we need. We probably should use some system stuff as FWPD already does with sysfs. Then the question is like how we validate presence of the processor features, if this is platform TXT capable, if SKE works, and then the question is if we have ACM modules, which should be like ACM modules for Intel and SKL for AMD or whatever there will be for AMD, because there are other there may be other implementations. Finally, we can check PCRs if those were populated, but because that means if there was early launch, then those should be populated, and we should be able to find valid values in those PCRs. Yeah, and while doing this presentation, I look at the specification, and I gathered some discussion points. So first of all, the claim of the specification saying that this mechanism to be trusted, this rating information should be distributed in centralized agnostic database such as the LVFS. I'm not sure if LVFS is agnostic enough for everyone, but maybe this is for VPAP. And maybe there should be other models. So for example, I thought about a more decentralized model based on like something, I would not say web of trust, but I don't know, even blockchain, yeah, or something similar that everyone contributes, and if there is consensus, then that means given set of measurements is good enough. Of course, this also can be abused, and I believe community and users and business should be able to select their own method of judging and giving these levels. So the problem here is, of course, that there is arbitrary decision about, okay, this level, those features enabled in that way. So that's kind of what is my point here. And FWPD LVFS direction, which right now going into bigger and bigger updates. This is just for your information. For me, it is somehow concerning because right now I see that FWPD LVFS pursue BMC updates, which is like full-blown Linux update or whatever will be inside BMC. And that's on one side, this is very interesting, but I would want to ask what would be next. Maybe, I don't know, full Debian updates over FWPD. That's, I don't know, like where is the limit for the for extension of these capabilities. Then, of course, I don't know if this is good or bad, but to some extent it is important that we cannot use any additional hardware, software, or we cannot enforce configuration change on the user to do the HSI check, which is, of course, like kind of hard because some features would probably never be we would probably never be able to verify some features out like from operating system from inside. And of course, what's with the KubeOS or any hypervisor-based environment? Yeah. Or maybe on the other side, we should talk with silicon vendors and various players in security ecosystem that verification of the security properties should be possible without external hardware, without additional software, without some configuration change. I know that Intel got this additional ACPI table, if I recall correctly, which in future platform, I believe starting from Elkhart Lake, will report some statuses of like what kind of security features this platform will be capable of. But this still is dependency on the quality of firmware implementation. Yeah, and what so this is the question that I had before. What kind of level on what level we would like to check the RTM, and then what about different boot flows, like modern open source firmware boot flow that I presented in FOBNA presentation? Or how we will judge those? Like, in my opinion, those are way more secure in comparison to proprietary ecosystem which we have right now in most cases. But still, there is no place right now in FWPD for those checks. And of course, like this is open source project, we can contribute something. So that's it. What do you think about? about LVFS, FWPD, HSI.
Well, if no one else is going in with a question, I'll ask mine. I did take a look at the spec, and it is very, very Intel focused. I think it would benefit massively from having some other vendors provide some input there. On the actual HSI level, I think there needs to be a split between presenting the capabilities and taking a decision as to how secure they are. Obviously, collecting the information is a prerequisite to being able to judge how good it is. And collecting that information is useful irrespective of where the arbitrary lines get drawn between the 5 different levels. One thing I would note, however, for example, take SET as an example, is control flow enforcement. There's one capability that says SET is available in hardware, and there's a separate one for SET is active. And that seems weird. Yes, it's useful to know that you have SET available on your hardware, and it's useful to know if you're not using it. But using SET is a dynamic property of the operating system. You could have a bug that accidentally turns it off, or something like that. So just because you run it once and get an HSI 4 level or something like that doesn't necessarily mean that 2 seconds later there isn't a kernel bug and it all falls apart.
Yeah, I believe the goal of the spec is rather for end user to have some measures at an arbitrary point, some checks at arbitrary point. I agree that's definitely, there are many concerns here. For example, your concern about like immediately after that something may happen. So definitely different environments like kubes environment, like hypervisor based environment can do something with that and mitigate that problem. But on the other side, we have right now also measures based on things exposed in sysfs, and like the question is how good the people coding sysfs exposed information are, and if they're not making any mistakes.
I mean, yes, one specific example there is under Zen. If you ask Linux whether it's vulnerable to meltdown or not, it will say no, not vulnerable, even when the system is vulnerable, because at that point, meltdown protection is a function of the hypervisor, not a function of the guest kernel. So in your example, if you were to run that under kubes, it would come back and say fixed even when the system was vulnerable. So I think
as well, you're checking for TPM, like what kind of version of TPM I have, and then of course like you have some emulation hooked, and it's saying like TPM 2.0, yeah, but it doesn't say like what kind of what kind of quality of TPM 2.0 you have. Yeah, is it hardware TPM? Is it like what's there? But anyway,
let me comment here. So one of the things you're getting to is the things that we've lost that's been around in trusted computing for a long time. You're talking about your mechanisms and what are the strengths of your mechanisms. So that's what you should be taught. That's the way this should be really couched is, we can look at what mechanisms are available on the platform. We can make assessments of how strong those mechanisms are. And then we can also take a measure of how well software, operating systems, firmware make use of those mechanisms. And so then you can come up with an assessment, a risk assessment of if you're using firmware version X with Linux kernel Y on platform Z, what your mechanisms are, how well the pieces of software use those mechanisms, and you can have a risk assessment for your platform at that point.
Yeah, and I believe we are quite far from that, from having that. But on the other side, still, when I try to discuss with Christian, for example, how we can check, how we can judge DRTM and how we can add DRTM checks, what kind of DRTM checks we should add. Because on the other side, I believe this also is, I would say, even from the marketing perspective, it's good, because having those checks there, already saying this exists and this makes some impact, you can add some documentation that has good reach. On the other side, there's building awareness of that this feature may be important, and then because you have this in tests, then someone can ask, and why on my platform this giving this bad results? Like, let's say level 1 tech guys who use Linux, asking vendor like, what's going on here, yeah, and why. And from that perspective, this is good, because this built awareness, this is marketing. And on the other side, we may also think really how to validate that, how we can be sure that this platform is DRTM capable in correct way, and prepared for that.
Right, which is where it's a little bit of, you're going to have to have some back-end knowledge set up in the system, right? Because a human is going to have to determine whether or not AMD's DRTM mechanism, what the strength of that is by looking. Is it in hardware? Yes. How does it communicate with the TPM? Right. You can look at all these things. You can do the same thing for Intel. You'll be able to do the same thing for ARM when the capability comes out. So those assessments can be recorded in the database, so that way when you run your test on the other side, it can say, okay, I'm on an ARM platform. Does it report having the ARM's DRTM capability? And that gives you, that allows you to take an assessment of what the strength is that you have there. But again, as what Andrew's pointing out, even if these mechanisms are present, you need to know how well the software is using it. And so you'll need to be able to make, people are going to have to take assessments of software and make that, store that in the back end, so that way when you do your detection, you can look up what software do I have present, and does it make adequate use of the mechanisms.
The reality is that what will happen is, over time, your backend will be updated and saying, oh, we happen to know this version of Linux is vulnerable, or, oh, we happen to know this version of the SLB is vulnerable, or, oh, we happen to know that this specific platform shares an SPI bus between two things and you can interpose on it, kind of thing. So I think the reality is that what you're doing for remote attestation has to end up being dynamic on the server side. An exact same system attesting itself at a later point might come up with a different strength, or a different different evaluation of its security, because of new knowledge that has become available about the platform or the specific software and firmware configuration being run.
Right. That's what you're trying to get at, is what your risk is. Right. That's what we're always trying to find out. What is our risk that our set platforms will remain safe or uncompromised?
Well, no, it's also whose signal databases do you have access to? So if I have access to a non-public source of vulnerabilities, and my attestation server, just discovered a new signal, then the attestation can fail.
Correct. I mean, your assessment of risk is only going to be as good as the evaluation, your data you have, right? That's your metric that you're using to measure everything with. So yes, I think the key point there, and this is probably something, Piotr, you guys should really be pushing on this, right? Because this will lead to it, is that we want to have strong assessments and a rich set of assessments being made available in FW updates databases.
It's like like the movie Weekend at Bernie's. So basically, every product management team should have like a Bernie mannequin at the table for the undisclosed 0 days that are part of the product management discussion, that are going to affect your customer risk assessments, but no one ever talks about them. They're kind of invisible. Until then, they knock on the door and say, hi, I'm here.
Yeah, but you can't quantify the unknown, right?
Sure, you can all the
But
time.
you
Insurance
can.
does it every single day.
Well, yeah, so if you want to do actuaries, right? So if you want to do actuaries, but remember how actuaries work. Actuaries work based on the fact of how often, if you wanted to do it in this state, you would look at how often you got, how often does, say, Intel wind up having 0 days, right? That's what an actuary would do. And so therefore, if you're using an Intel product, you would have this risk of a potential 0 day.
There's lots of other ways to mitigate. There's lots of other ways to mitigate risks. Like you could go and get an investment from the attacker.
Yes, there are ways to mitigate the risk.
You can move to a country where the attacker is located, and therefore they won't attack you because somebody's going to whack them.
Yes, well, but that's risk mitigation as opposed to risk assessment, right? You have to assess your risk, and then you have to, once you know what your risks are, then you have to decide what your mitigations are going to be. Your mitigations may be, all my attacks come from this country at Y, so I'm going to go to country Y and I'll knock on the door of everybody that I find out banging on my system, right?
I think the key thing is the attestation event draws upon different data sources, and those data sources have jurisdictional implications and organizational implications and financial implications, which are all non-technical. So we have an extremely technical activity called attestation, which has 80% of it is non-technical. So we just need to remember that one small factor.
Yeah.
Yeah. So I on the other side, I think it's okay. Valid mechanism, like strong mechanism for verifying things is one side of the coin, but on the other side of the coin, awareness is also important. And I believe if we were trying to convince Richard to merge patches which will contain HSI tests for DRTM or whatever different stuff or DRTM related thing, like even presence of ACM or presence of TXT feature or whatever, I don't know, correct IOMMU configuration, then he will probably try to check that to some extent, but then eventually only people really deep into the like DRTM environment can really understand, okay, is this SMM protection good enough? Is it and then of course then is the mechanism that confirming this protection is good enough. And I don't think this complex nature can be easily introduced into FWPD and quickly introduce it. But some things can be quickly introduced, some checks can be quickly introduced, and that can bring attention to TrenchBoot project to the needs of DRTM. And that's my point. That's my point. Just to slowly build attention of this group.
So on the subject of IOMMU specifically, I meant to call this out earlier. IOMMUs are fiendishly complicated to get right. First of all, you basically have to trust the ACPI table that is written for it. And if the ACPI table is wrong for the platform, you're insecure. But even if the ACPI table is correct, and realistically that could only be checked by having some sort of sideband method that can check the ACPI table presented on boot, that needs platform-specific knowledge to know what the ACPI table looks like. Even if the ACPI table is correct, there are a million and one things you can do wrong in the kernel that will end up with slightly weak implementations, or a bug in a corner case here or a bug in a corner case there. So I don't see IOMMU enabled as a useful metric. It's perhaps having one enabled probably means you're better than not having it definitely not enabled, but just because you've got it enabled doesn't actually speak to any security.
Andrew, I would definitely like to discuss that during the VPAB, because if we
you see, FWPD is missing a new level called the AC level. It's a special category of risk assessment.
Andrew Cooper level. On the other side, one last comment, Daniel. I'm just saying that Linux guys tend to assume that BIOS delivered whatever was needed to deliver. And we know that, and we heard that on LPC. So if we will use their logic for convincing them about IOMMU, you already have like something. Yeah? You already have something, despite the, Andrew, you will discuss the quality of that. But on the other side, we will have something inside that move us in the direction of showing more and more features related to DRTM.
All right, so just as we transition to the next one, I want to put up the splash screen here to remind people about the VPub afterwards, and then we can get transitioned into Stuart's talk if he is ready.
Just before you do that, so existing capabilities, tool sets, projects that are similar to FTP-PD, the ones I can think of are and they're in a spectrum, right? So you have like whatever AMD and Intel use before they ship hardware, or OEMs use to test hardware security. Then you have something like Microsoft Secured Core, which is an OS certification. And then you have something like Metasploit, which is, red team collection of breaking promises made by vendors. So where would you say FTP-PD is in these three things? Is it closer to the Intel AMD thing, the Microsoft Secured Core, or Metasploit?
Yeah, we can discuss that during the VPub. Try to build a spectrum.
All right, Stuart, you should be able to try to share now.
Okay, let me share. All righty, can you guys see that?
It should be, it'll be onto the stream in a moment, but yes, it should. It's good. You're good.
Okay. All right. Hi, everyone. I'm Stuart Yoder. I'm a system architect with ARM and focused on platform security, especially boot security, and been working on DRTM recently. And so what I wanted to do is give you an update on kind of where things are. So it's still definitely early days for DRTM on ARM. I want to give you an update on just at a high level, how DRTM maps onto the ARM architecture. And there's definitely some differences compared to x86, and give a brief update on where we are with the spec and implementation plans. And then I do have some discussion points that, some of this, came up at Plumbers if you attended the session there. But I think there's a few interesting things to discuss that, have come up in our work at this point. Okay, so with that, I guess this picture is, I guess my view of how DRTM works, where kind of using some of the terminology from the TCG spec, where there's some preamble code that is going to try to launch and measure a target payload of some kind, which we call the DLME. And so on x86, that launch is, are these special instructions, for example, SENTER or whatever. And then the implementation is responsible for, I guess, one, making sure that the system's in a state where it can make an accurate measurement of the target. So, you're only running one core and there's not ISRs going off and that kind of thing. And then you make your measurement of the DLME and transfer control to it. So, pretty simple. And so what I want to show is how we map this onto the ARM architecture. I guess this is, I guess, forgot to flip forward to this. So yeah, there's this safe state you're in when you begin the DLME, where the DLME is able to, kind of establish a, the safe place to run. It can, enable things as it needs to in order to kind of move towards the OS runtime. So on ARM, there are, like on ARM v8 at least, which is our higher end ARM cores, there are 4 privilege levels. And so some of these are typically not going to be, actually, I meant to start my video, which I will. 1 second. Sorry, I meant to start my video, and for some reason it's need to change the camera here. Okay, now I'm on. So with the ARM privilege levels, we have this secure set of privilege levels where you have a layer of secure firmware at what we call EL3, and then potentially trusted services that may or may not be there on any given system. I mean, it's analogous to SMM in some ways, as far as, you know, that the secure versus non-secure side of the machine. And so there's a lot of variety you're going to find on ARM systems with what may be in the secure world, the secure side of the machine, but there's always going to be a secure EL3 firmware layer. And then it's the non-secure side of the ARM machine is where things like UEFI and your OS run. And so, so the scope of DRTM on ARM is on the non-secure side of the machine. So we're not trying to, you know, establish a new TCB for the entire ARM machine, but it's really, we're focused on the non-secure side. And the reason for that is it's the UEFI firmware in particular that is arbitrarily extensible, and you know, and in the way that it's described in TCG architecture, there's this gap, right, where you you start maybe with your SRTM boot flow, but then you get to a point where as more option ROMs get loaded and extensible components get loaded into the boot chain, your TCB grows, and it's difficult to kind of rationalize the TCB. And so it's the non-secure side of the machine that, you know, is kind of the scope of what we're trying to focus on. Okay, so with that, the way this maps now onto ARM privilege levels, kind of going back to our original picture, is that it's the highest non-secure privilege level, EL2, that initiates DRTM, and we use special instructions called SMC calls. That is what EL2 uses to kind of request firmware services of our EL3 firmware. And so that's how it's initiated. And then there's a few ways the DRTM implementation could be done. And one is it could be all done in EL3 firmware. That would be like the architecture allows that. There's also the possibility of having simply the root of trust in EL3 and then having the rest of it in what we call the DCE. And that's similar to like the SNet ACM on Intel for TXT, where that's going to run at the same privilege level as, you know, your preamble and your target payload. I guess another aspect of this is that the architecture also allows this DCRTM, which is, you know, the root of trust for DRTM, to also be in a separate coprocessor. And so the way it would work is, you know, the launch would happen, and then there would be a shim at EL3 that would initiate DRTM on the separate coprocessor. And so, you know, you in this case even have kind of a greater confidence that you have a small TCB that you're instantiating, and you don't necessarily have to trust the EL3 firmware, you know, its integrity. I guess in this picture also mentioned that, you know, as far as who supplies components here, you know, it's going to be the OS vendor, you know, that owns the preamble. At least that's the way I would view it, as the, you know, it may be OS specific, like Linux or Windows specific. And then the DLME, the target payload, is also going to be OS specific. And the other components here, the DCRTM, the DCE, or the security coprocessor implementation, we don't dictate whether that is going to be coming from a silicon vendor or from like an OEM who puts a system together. Because I guess the ARM model is that we license IP to vendors or the architecture to vendors, and we don't dictate, exactly how they do this. And so ARM is not going to provide, an ARM signed set of firmware components or a DCE like a processor vendor might. So it's going to be the silicon vendor or possibly the OEM who, is kind of integrating the system together that are going to be signing some of these components. I know one of the things that was mentioned earlier in some of the talks was, questions about, openness and whether these components are going to be open source or not. And I guess, the point I wanted to make here is that, ARM doesn't really control that. And so, hopefully vendors will open their firmware, but it's not something we can dictate. And, it's going to be just kind of on a case-by-case basis as to what gets opened and what isn't. Okay, let's see. So in our architecture, when the DRTM launch is initiated, there's a set of parameters that we pass that are available to the client. There's a set of launch feature bits that can be selected, and then various things about the target payload, its entry point, the size of the region, and so on. And then there's a memory protection table that is passed that describes, like, I guess we don't have a hard-coded or specific region that is protected from DMA. We allow the client to select that. And so the options are either all DMA to any address is prohibited via SMMUs, which is our IOMMU device. Or we also allow in the architecture to have some kind of vendor-specific protection scheme that is distinct from using IOMMUs to kind of protect a specific region if they need to. So yeah, that's the data that is supplied as an input to the launch. And then after the measurements happen, DRTM does its thing and measures, the DLME and other system state. There's a set of data provided to the DLME that it can use, how it wants to basically defend itself. So that includes a list of what memory is protected, an address map of the system. And so that address map is basically, a DRTM certified map of what is normal memory, what is device memory. So for example, if an attacker, back in UEFI firmware, tampered with the UEFI system map and reported that some IO region that they control was actually normal memory, and then the OS tries to use it, this mechanism of providing a DRTM address map of what is normal memory helps mitigate those kinds of attacks. The DRTM event log is in this region, and also we provide a set of ACPI tables that are basically, again, DRTM verified, and those include like where the TPM is located, and the IOMMUs in the system, where they are, PCI, IO space, and also interrupt controller information. So there's a set of data that's provided that, again, the DLME can choose to use how it wants. So that's the overview. There's a specification that is very close to being public, beta spec. We've been working on it over the last year, and I think what I reported before was that the target was to release it this fall, which I think we're still on track for that. It's there's been some late feedback that has taken a little while to close, but I do expect in the next month or so to have the beta spec public. As far as implementation goes, So what ARM is working on here is going to be a proof of concept kind of reference of the EL3 firmware part of this. I mean, that's kind of our starting point is, and we plan to make that's going to be open source, part of the trusted firmware project. And so some of the details of exactly how we're rolling that out are TBD, but what I'm hoping for is that we'll have a side branch of trusted firmware where the initial proof of concept code is, and then the development happens in the open on that branch versus on just having it all being done internally and then kind of pushed out later. So I mean, roughly, by middle of next year, I expect to have a reference implementation that's publicly available. But you may see that in development over the next 6 months. Let's see, anything else I want to say about that? So that's my overview and update. I guess one of the things I wanted to have some discussion points about was some of the feedback that I've been getting from, say, some of the ARM Linux kernel developers is about the data that your target payload is getting. And so one of the key concerns, and I think this may have been touched on earlier in one of the talks, was about UEFI provided data. And so I know, if I remember right, it was mentioned that UEFI scenarios are kind of potentially problematic. And so the concern is that the firmware provides ACPI tables and they're effectively untrusted, right? Because they came from the firmware, and as well as runtime services that an OS may use. And how do we rationalize an OS that's been verified and measured, but now has to rely on untrusted data that potentially could compromise something? And so, yeah, that I don't know if I'd be curious to hear, maybe have some discussion about that, about for TrenchBoot, does your threat model include what data Linux may use that maybe hasn't been verified or is potentially suspect? So yeah, I don't know. Any thoughts on that from anyone?
So obviously on Intel, you actually get the ACM does do a degree of verification like you're talking about here, and passes that information along. Now, with that said, it doesn't do anything for your runtime services. The runtime services is still a lesser trusted software that is still in memory, that you may or may not want to continue to use. In the cases where you may want to continue using it, the reality is that whoever's building their DRTM solution needs to find a way to constrain and control those runtime services. For instance, one of the approaches I proposed to using DRTM with Zen is the fact that we could actually create as a solution, you can actually have a runtime services VM, which is the only one that's actually allowed to make any calls into runtime services. And then you have to, then that allows it to be run within a VCMS and within a VM. And you can control what memory accesses the runtime services could actually have.
Okay. So I guess, today, as far as the ACPI tables go, so, I don't know how many ACPI tables Linux consumes or uses from the firmware, but it's my understanding that, we provide 4 that we consider security critical, but there's questions about whether that's enough. And I guess, have y'all looked at, for the tables provided by TXT, has there been any kind of study as to, one, I guess, do you use those tables currently, and then, 2 is is what's provided enough, for Linux to kind of really, not have any vulnerabilities?
We'll get to that later.
Okay.
No, the reality is that there is information provided, certainly on the Intel side, but it's bordering on too little, in my opinion.
Okay. Yeah, I think that's. I mean, we've tried to make the ARM. I guess kind of flipping back here, we provide these validated tables here, and to make it extensible so that, since we are implementing a lot of this in firmware, if there were additional tables needed, to try to be able to make it extensible so that we can accommodate that. But yeah, I think that's kind of a question, is like what is needed, and I think I don't have an answer yet. I mean, I haven't had time to dig into there's some like 15 to 20 tables, I think, at least for Linux on ARM, that may get used, and to look at each of those and say, well, if an attacker modified this table or tampered with it, what damage could happen?
Yeah, well,
on x86, you've got at least two different virtual machines. One that lives in the AML with the DSDT and SSDTs, and then you've got the ERST, which is a different virtual machine for firmware executing arbitrary instructions in nominally the kernel environment. So there is a very large amount of stuff we do not trust in the ACPI tables. And part of the problem is that there is a reasonable amount of system critical information that you can only obtain by executing arbitrary DSDT code.
Right. Which is, again, from that perspective, that's why I've always recommended that access to any of the firmware services, whether it's the runtime service or it's the ACPI tables, you need to do within a constrained environment, so that, as Andy pointed out, that it's going to be running at kernel privilege level, so it could manipulate anything about your system that it can get to. So you want to make sure you constrain as much as possible. As to your specification, I think it's my public opinion on it, we can talk privately, is that you should, I wouldn't go down the road of trying to specify every type of table that whether you should or should not provide. I think what you've got now is probably the right path, which is identify just the core critical ones that's absolutely must be done, and allow that to be in the spec, and make sure that the data structures are flexible such that any number of tables could be passed based on perhaps an OEM or whatever called chip manufacturer decides should be protected because they have some piece of critical information.
Right. Okay. On the AMD implementation, so if I understand correctly, the AMD hardware implementation does not provide data, but I guess it's kind of your secure loader is kind of the equivalent, right, of of this component here that
yes,
may provide things. And so I guess, do you guys have a spec of some kind that describes, like, when your secure loader launches the DLME, like what is passed, and do you guys provide like any data, like tables or anything? I was curious, like, how that worked on AMD.
Yeah, so that's been one of the challenges we've been dealing with. So this goes back to the earlier discussion for those that didn't happen to be there, over the Intel signed ACM versus AMD's model of user provided DCE.
Right.
Right. So one of the benefits that they get with the ACM is that they can then put chipset specific data inside of it for the verification. That's how you get the verified tables coming back out of TXT.
Right.
Whereas now, if in your DCE on AMD, you have to, whoever's the implementer of that has to then figure a way of validating that information when it's inside that protected environment that it runs in. As far as the protocol passing that over, there is a loose protocol we've gotten defined that we use in our secure kernel loader, the SKL that you may have seen discussed today.
Yep.
That's an open source version of this, of the DCE for AMD. We've been trying to build it for flexibility. There's been some challenges with AMD, so we've got to overcome those, and then kind of we have an effort to try to finalize what that protocol eventually looks like.
Okay.
One of the things that we are trying to do, because we want this, again, one of the goals for TrenchBoot is commonality, right? So we don't want to have a wildly different interface coming across from the DCE to the DLME, i.e. we don't want to come from the SKL to Linux to look totally different than what it looks for Intel.
Right.
Now, can we mimic it 100%? We probably do. We're going to do our best approximation of that, right? But the idea is that we want to have that looking very similar as much as possible, because it reduces how much logic we have to introduce into Linux's setup kernel.
Okay.
One very minor point whilst you're on this slide. So this slide is accurate of the AMD representation. The DCE runs as regular supervisor code on the processor. It is not accurate of Intel's representation. On Intel's representation, the DCE runs in ACM mode, which is a different mode in the processor, which is more privileged than SMM mode. Yes. So really, DCE should probably be an EL4 logical position in this diagram. It has more privilege than EL3.
I see.
But yes, that was just a minor thing.
Okay. Yeah, that's helpful. Yeah, I wasn't aware of that. But that's helpful to know. But yeah, I guess, that's really, I guess, what I wanted to cover as far as, but I'm happy to try to answer questions at this point from anyone on, I guess it's still early days for us. We're kind of, getting the spec complete, been doing some POC work, proof of concept work, and, moving towards getting some open source code out there. And so,
right. So obviously there's two questions that immediately follows from that. What class of devices will be able to run this, or class of processors? And then two, what boards out there are available that somebody could actually start when you guys get your prototype out, reference implementation. Right. What could somebody use that on to start prototyping, say, a TrenchBoot solution for ARM?
So so currently the proof of concept works where we've been doing using this FVP model that ARM has, that we do a lot of our reference code on, as well as QEMU. And so the initial work that we're doing at this point is being done basically on simulators. I guess, one other system aspect to this is that on an ARM system is that on a typical system that, say you have a discrete TPM chip, on many systems, the TPM can be directly accessed by, your EL2 kind of application processor code. And the problem with that is that, we have to protect locality for, and we can't have Linux, resetting the dynamic PCRs or doing something with the TPM. And so there's a set of system requirements that we have in the spec. And one of those is that the TPM has to be protected, so that, in particular, it's the DRTM implementation that can access locality 4 to kind of reset the dynamic PCRs and make measurements using locality 4. As far as hardware that, I guess that would implement that, I guess I'm aware of, some of the systems from Ampere, it's my understanding, do that. But I'm not sure if their firmware is open or not, where you could experiment with that yourself. I guess there's a question, I guess, about as far as TrenchBoot based experiments, whether or not, if you just want to get things functionally working versus you want something where, the TPM, cannot be accessed by say Linux. I'm aware of, if there's a few systems that support TPMs that are, easily available. One is the Synquacer system from Socionext, has a TPM plugin that, is a possibility. But yeah, I think it's gonna, we're as far as when you're gonna see a hardware system, with full security, with a protected TPM, with DRTM on it, I guess I don't have an answer for you there. I think what you're gonna see over the next 6 months is going to be either QEMU or FVP based, platform, and okay. We'll see real hardware, after that. And also, as far as the type of processors, this is ARM v8, 64-bit processors only, and so it's the A profile processors for ARM v8. Versus, so it's not going to work on smaller microcontrollers and things like that.
Okay.
Presumably it will be up to the individual silicon vendor as to whether they want to include this technology at all.
That's correct. That's right. Yeah. So yeah, this is not part of the ARM architecture. So, if you follow ARM architecture at all, there's I think every year or two, there's, a new, ARM 8.5 or 8.6 that adds additional features. And so this is implemented using existing ARM architecture mechanisms. And so it's a separate spec. The base level of this is going to be firmware based, where it's, as long as your system hardware has the right prerequisites, like a protected TPM, for example, and all your devices must be behind an IOMMU, for example. If those requirements are met, you can implement this in firmware. But yes, it's going to be up to individual vendors whether they choose to do it. And so that's right.
That brings up a good question, which I'm sure you probably can't answer, but I'll ask anyway. Do you see this falling into the ARM architecture specification eventually?
Not at this point, because right now, the ARM architecture is about the instruction set, and so at this point, we're using the SMC calls to initiate this. Even if you want to have a hardware-based root of trust, like having a security coprocessor be a root of trust, which kind of takes care of hardware, resetting the cores and starting the initialization process. Even in that case, you initiate it via an SMC call. And so at this point, I'm not aware of ARM architecture changes that would be needed. And so, yeah, at this point, I would say no. It's gonna be a, there's a set of firmware standards we have, and this is kind of probably going to be in that category.
Okay, I just asked because it's just, it's great that it can be supported in this manner as opposed to becoming ubiquitous, kind of like how it's almost ubiquitous on AMD, right? Every AMD processor has the capability as long as they have the VM capability. So
yeah, it's every processor since the K10, which is what, 14 years old now.
Yeah.
So every single AMD processor since then has all of this in it. Whereas on the Intel side, we think most of the processors have it, but it only actually exists on the vPro SKU.
I don't know if it's actually in every processor, because I've been told certain details that keep it from actually being on every processor. It is definitely on
I think the principle is it would work on far more processors than it is nominally advertised for.
Correct. Yes.
And there are marketing reasons why we can't currently use it in cases where we would prefer to.
Yeah, I think what's going to I think it's going to be probably pull from the market is going to, you know, cause people to implement this on, you know, for targeted systems. You know, I mean, if there's demand, you know, for an OEM to do it, I think, you know, you'll see them take the steps to do it. You know, as you know, I mean, Microsoft and their Windows Secured Core initiative, I mean, DRTM is a part of that. And so, you know, anything that wants to run Windows, any system that needs to do that will, you know, you'll see it there, I think. And so, but in the end, yeah, the ARM you know, SoCs are in many segments from, you know, small to large. And so there's definitely going to be a lot of variety, and you're not going to find this, you know, pervasive, I don't think.
Right. I wasn't expecting it to be down all the way into the M class and things like that, but it would, you know, yeah. There's optional instructions in the, at least it used to be. It's been a while since I've seen it, but it used to be optional instructions that not every core had to implement. So, but regardless, right. All right.
Okay. Well, I mean, I'm happy to take more questions, but I think, you know, that's it from me there.
Okay. All right. Thank you so much.
Just a note on the hardware, the hottest laptop silicon right now is the Apple M1, and the former Apple M1 team is now at Qualcomm, and in their investor announcement today, they said in 2023 they will ship ARM laptops for Windows, you know, which will be competitive with Apple silicon. So that'll be your DRTM device of choice.
Yeah, I mean, obviously, Microsoft's going to be a huge force in getting DRTM implemented more ubiquitously.
Yeah, it's the first time we have a date, though. So 2023 for commercial hardware.
Okay.
So with respect to the comments on the ACPI tables that get forwarded upwards.
Yeah.
There was, must have been about 4 or 5 years ago, just kind of an anecdote on all of this. We reported the bug to Intel when we were working on that end of the chain. There was a bug in, of all things, the printf precision specifier in the implementation of the Tboot code that allowed whoever controlled the ACPI table to inject up to 255 bytes of their choosing into Tboot memory after the senter instruction was executed. So, you know, the notion of being able to, we reported it to Intel and it was quietly fixed and then it disappeared, never heard anything. It had the odd effect of printing happy face when the ACPI information was printed by Tboot. So we ended up calling it Happy Alaska. And of course, if it was, we didn't realize then that you could make money by having websites with catchy security vulnerabilities on them. But it sort of underscored that you have to be cautious on what you're ingressing with respect to your ACPI tables if you're going to make decisions on them. And you need non-buggy code, of course.
Yes.
That sounds like a very fun one to go and exploit.
Yeah, we never spent any time on it. We had other things we were working on, but it was
very familiar with that problem.
Yeah. Yep. It was kind of one of those that you find interesting that you stash away in your portfolio.
Thanks for sharing it.
So, yeah, we've got a few minutes before the start time for the next talk. So we can just continue to have just an open discussion until that time, just so that way that starts on time for anybody that's looking to get to that, wait for that specific talk, or is not showing up until that specific talk. So,
how about the Pine phone?
The Pine phone. Yes. That would be very interesting since it is an ARM 64 device. A class. I believe there is a TPM on it, or well, you could at least do at least a firmware TPM if not. And in theory, it has open firmware. So
DRTM on the smartphone.
Yes. Yeah, no, that would be really nice to have. And pair it with your fob now, and now you know that your phone has not been compromised through an external attestation.
Actually, that's a good.
That was why I was asking about NFC to Piotr was right. It'd be interesting to be able to just tap your fob nail to your phone that has DRTM on it and have a red or a green light go. Or blue and whatever the other suggestion was for 508 compliance.
Blue and brown, it's the same reason we use that for wiring in this country.
Yeah.
So do people get the sense we're sort of heavily involved with a new model for, let's call it dynamic mandatory access controls? And I know Mimi Zohar at IBM, and I watched the Linux kernel, been involved with it pretty heavily for a lot of years. Do you get the sense that people that are building, say, from after a KExec upwards are willing, and again, it comes back to market pull, are willing to trust whatever keys the UEFI certifies? And if the keys are correct, it assumes that you can build your secured architecture on top of that?
So
I think it's tolerated at the moment because it's one of the few things that works reasonably well. I think if you look at where Microsoft are trying to go with the secure core and Pluton and stuff like that, it's very evident that they prefer a better level of trust.
Yeah, if you watch any I wouldn't say any, but there have been multiple presentations by Microsoft individuals where they basically refer to UEFI as a dumpster fire. They do not want to trust it. That's why DRTM is part of Secure Core. And there's even, when I first started the TrenchBoot project, there is even an approach that I proposed with doing within AMD, and you could probably do it with Intel as well, is actually do a method where you have a key that's wrapped up as part of your initial measurement from your DRTM chain. And that way you now know if that DRTM was correct, then you have a key that you can then use further on if you want to do key-based validations, certificate or public key validation kinds of approaches for your system. That way it basically inverts the way measured boot works for SRTM, right? Today it's verify then measure. This would actually flip it around and do measure then verify. So the answer is you can build on a house of cards if you want. It will come tumbling down.
Well, it's also who is going to be doing attestation servers. Like everything we're talking about here depends on a future where there are multiple attestation servers. And
well, go ahead.
Yeah, I mean, assuming there's not one big attestation server in the sky for Earth. But if there's multiple attestation servers, then, essentially so basically, let's say there's 5 attestation servers with different a spectrum, and one of them decides to trust UEFI and the other one doesn't. It's only, say, using silicon roots of trust with a custom dedicated enclave inside the SoC. Attackers are going to attack systems verified by all 5, and some are going to win and some are not, right? And so whoever wins, their attestations are not going to be trusted in the future.
Well,
it's a self-correcting problem.
Yeah, I mean, honestly, I would want to see a future where we have a disaggregated attestation with effectively rings of trust across them. But the reality is that, you know, well, some of us are aware, you know, Azure is moving that way. Azure has a whole attestation solution that in order to interact with it, you will have to be able to attest to it. And it's being built around DRTM and Pluton. So these are realities. Whether they become the only one, hopefully not, but.
So I think you're going to end up with a different one per each major cloud. But you look at the way you authenticate yourself online at the moment. You've got GitHub acting as a source of identity. You've got Facebook and various other services like that are acting as a third-party source of identity. I think the reality is that when you start getting Azure forcing the issue with attestation right from the Pluton processor in your Pluton crypto processor in your CPU all the way to the cloud, you'll get similar things in other clouds. And yeah, you can roll your own, and it probably won't have the same amount of uptime as one of the big cloud ones.
Yep. So, okay, it's time. So I'm going to go ahead and start getting my slides up, and we'll roll into the next one. All right. Greetings, everybody. My name is Daniel Smith. I am with the TrenchBoot project. Today, I'm going to do a bit of some review and then go into Linux Secure Launch of how and why. And we'll talk about some things that are coming up and some advantages to the approach that we have. And then we can wrap up today's sessions. So I'm going to just dive right into it. So let's get into launch integrity so we can have a good common understanding. A lot of these terms have come up throughout the day. Some have definitions that have been given. So I'm going to try to set a solid foundation for us all to have an equal terminology to discuss what it is that Linux Secure Launch is providing. So we're going to go through some core concepts. We're going to get what is a system launch, what is a dynamic launch, what is system integrity, and thus underneath system integrity, what are the roots of trust for measurement chain? So system launch. So typically most people think of system launch, they tend to think about static launch. This has been the way PCs have started forever. You have a power event that you have an initialization event. In the general sense, you have an initialization event, which is typically in hardware, that is followed by software taking control of the system and bringing the system into a running state. So static launch is the one where it is about the CPU coming out of reset and releasing control or turning execution over or starting execution within the system firmware. To bring it to a running state. This is static because this is in terms of the power life cycle of a system. This is only done once. It's only done one time and it's fixed at the beginning of the power life cycle of the system. Then you have dynamic launch. This was a capability that was introduced roughly in the mid 2000s. Which allowed, Intel was the first one to do so. Hold on, sorry. The Intel processor introduced this new capability called a dynamic launch. What it allowed for you to do is to have a new initialization event that was fired by an instruction, which was called the dynamic launch event. What that was supposed to do, or the intention for that, is to actually bring the system into a known good state, bring the CPU into a known good state that you can then start executing a trusted bit of code. That is what your DCE is. So your DCE is this trusted bit of code that's supposed to pick up from this known good state and bring the system back into a running state. So unlike the static launch, a dynamic launch can actually be done multiple times because effectively it's implemented via an instruction. So as you heard from we've talked about it today, and from an ARM and Intel perspective, it is a CPU instruction. It is for ARM, it is still in a CPU instruction, but it calls into the firmware, which I would recommend going back and listening to the ARM talk earlier today, if you did not hear it. So this is how a system can be launched, right? We have the static launch from power on, and then we can have a dynamic launch, which is triggered by a CPU instruction to bring the system into a good state. So when you do the dynamic launch, as I mentioned, you can do it multiple times throughout the power life cycle of a system. But dynamic launch usually is classified into two types of launches: the early launch and the late launch. So the early launch is specifically focused when dynamic launch is used as a transition from the static launch into your final operating system. This is the approach that everybody is familiar with, right? You boot through your SRTM, through your firmware up to your bootloader, and then your bootloader or a secondary loader then initiates the dynamic launch. A late launch is actually where the system has been under execution of some final operating system, and you need to transition to a known good state to perform an operation or to transition to a whole new operating system. The limits are only to your use cases, not to the capability, because at this point, at any time, you can go to a known good state, and then you can transition back to the software that started you back to the known good state. This is where things like Flickr and other capabilities have played this game of executing outside of the purview of their operating system that they're running under to do controlled operations. So once you have your two forms of dynamic launch, how do you establish integrity? How do you use these to establish integrity? Well, one thing needs to be understood is there are two types of integrity we can have about a system in terms of the software running on the system. We can have our load time integrity and we can have our runtime integrity. The load time integrity is specifically about determining the integrity of the entity when it was loaded into the system, when it was brought into memory before it started executing. So anytime you're doing load time integrity and you're reporting about that load time, that integrity assessment that you did, you only are assessing what was loaded. You make an assumption that what was loaded continues to be running without compromise. This is where you come to runtime integrity. To address that assumption, you then have runtime integrity capabilities that are about making integrity assessments about software that is already in execution and has been executing on the system. Once you have both of these together, you can actually make a much stronger assertion about the integrity of your system. So where does that play into? Well, that plays into these roots of trust that you hear talked about all the time. So roots of trust for measurement in particular. So when the system launches, right, once a system launch occurs, you start to take an assessment. You're going to start doing an integrity assessment of the system as it's coming up. And when you're building this chain of assess, execute, assess, execute, this is a transitive trust, which is often referred to as a trust chain. These chains start from have a starting point. That starting point is your root of trust, because that starting point is assumed to be good. And then you build from that. So at any point, that assumption becomes the mechanisms behind that you're relying on to make that assumption fail, then your whole chain fails. This is what we constantly see when secure boot gets compromised. There are assumptions being made, and then those assumptions are broken. The same thing has happened with DRTM. When you see your break, you'll see, if you track it down, you'll see an assumption made, and that assumption was violated. So when we look at the static root of trust for measurement, this is the trust chain that is built up from your static launch. Now, because the way power on happens, the CPU goes from reset to immediate execution of code. Therefore, that entity that's starting the launch cannot function as your root of trust. So you usually have to have something that is either an interposer, or you use you spin back into some hardware coprocessor of some sort, or a pseudo hardware coprocessor, i.e. the management engine or something like that, to take an assessment of the system. And then at that point, you continue on. So in many times, again, this SRTM usually starts in system firmware. That's starting to evolve. We're getting capabilities that are addressing that, but it's not ubiquitous. Whereas when you do a dynamic runtime or a dynamic launch, so a dynamic root of trust, your dynamic launch is initiated through an instruction to the CPU. Now you can actually see the CPU with a set of information necessary for it to do a measurement activity. So that's why typically in most DRTM implementations, at least definitely on x86, the actual instruction will actually, the CPU executing on that instruction will actually take the first measurement. This means that your root of trust is now rooted in hardware. This is what often this whole debate over being rooted in hardware means. It means that the CPU, the hardware, is what took the measurement, not the software from the firmware, even if that software came out of a flash ROM. So this is important to understand. So what are our mechanisms that we're relying upon to talk about this trust that we've built, and how complex are these mechanisms that we have in place? This was kind of hinted at earlier about pushing up the hill, right? You know, there's a lot more complexity in your SRTM than there is typically in a DRTM launch, because the chain is just much shorter and can be much more concise. So this brings me to why DRTM, which I've kind of gone into at this point, right? The fact is DRTM increases the load time integrity of the system. That's a fact. And another fact is that the sophistication of attacks are at an all-time high. So there is no reason a system shouldn't employ every integrity measure in hardware that is available. This is the crux of defense in depth. So you want to apply all the techniques you have and apply them in good ways. You know, in the past, you know, everybody tends, the common approach to attacking DRTM and trying to attempt to invalidate it as a capability has always been drawing these straw mans about SMI. But the problem is that, you know, a compromised SMI compromises the entire system, right? It doesn't matter whether it's your SRTM or DRTM, because an SMI attack is a runtime attack. It manipulates the running system as opposed to the actual loading of a system. So once you can manipulate the runtime system, you can then easily corrupt the load time. This is why it's important to close both of these measures when you can. And luckily, finally, Intel and AMD have actually started to deploy a capability to give us some runtime protection on our SMI and SMM parts of the system. So at that point, now we can definitely say that, you know, any perceived deficiencies in DRTM have been addressed, and there's no reason why we should not be looking to adopt this technology specifically to increase the security of our systems. All right, so off that rant for a little bit, just to finish up on, bringing some common terminology together here. So there is the DCE preamble when it comes to a dynamic launch. The DCE preamble is like it's named, right? It is a setup to set up the system for the CPU for the dynamic launch to start the execution of your dynamic configuration environment, the DCE. So for secure launch for Linux, right, this can be either grub or a kexec can function as the DCE preamble. And then it can actually call the CPU instruction, which triggers the dynamic launch event itself, which then begins execution of the dynamic configuration environment, the DCE. So again, on Intel, where we're at, and AMD, this is your ACM, or for TrenchBoot, our open source secure kernel loader, SKL, which is an implementation of AMD's secure loader block. Once that has finished getting the system up to a running state that can be handed off to an operating system kernel, this is where you get to the dynamic launch measured environment. The ACM or the SKL will measure this and then transfer control over to, in this case, it would be Linux. And you would come in through the secure Linux, secure launch for Linux entry point into the kernel, and we would allow that to bring the system up from the unique state that is caused by a dynamic launch. Okay, so now that we have an understanding of what some common terminology, we're all on the same page as far as words go now, and what are the componentries on here. Let's take a look at what DRTM implementations are, the major DRTM implementations that are out there today. And there's 3 of them, really. So the newest one has been Microsoft Windows 10, which, if you've heard us talking today, that's the Secured Core PC standard. The capability is being marketed under System Guard Secure Launch, and you can debate who picked that name first. It kind of came about around the same time, so it just so happened that's the way it played out. But at this point, the best implementation details on this that explains how it works for Microsoft was presented at OpCode Kenya in 2018. And their basic flow is that they have WinLoad, which is the existing Windows bootloader, functions as your DCE preamble, and it sets some things up. And I've got a pictorial that we can go through on this a little bit more detail, which then triggers the dynamic launch, and you wind up inside of a component they call TCB launch, which in some places I've seen referred to as TCB loader, and that is your DCE, or well, it's your late DCE or early DLME. It follows the the T-boot model, which you'll see. And then it'll bring you into the Windows kernel, which is your DLME environment. So again, like I said, TCB launch functions very similar to T-boot. It's effectively in a persistent exokernel that's always present, and it's there to basically manage the power events, because on Intel, it does matter that the power events are properly handled when you're entering and exit, or if you're inside of SMX mode, you need to make sure you properly handle those. Otherwise, you can result in a fault in the system. And it requires the presence of the new platform property assessment module for Intel and the equivalent capability for AMD. We'll focus today when we're talking about that specifically, which is to address the SMI-STM or SMM gap. This is the solution that brings this to bear. So how does this actually work? So this is the from Microsoft's own briefing. So I figured, go to the horse's mouth for the source truth on how it works. So as you can see here, you have WinLoad, and WinLoad basically pulls all the information it needs from EFI, from the UEFI, and it loads it into memory. Here they've labeled it as a RAM disk. I don't know exactly if it's a RAM disk or not, but it does. In their description, it loads everything that's necessary into memory to be passed across the trust boundary. And then it does a DRTM event. And that DRTM event lands it inside the TCP launch. TCP launch then can pull that information, validate it, measure it, and then launch the follow-on kernel, which is whether it's the Windows NT kernel or whether it's the Windows hypervisor. And that is System Guard really quick. So the next solution is TBoot. And TBoot was the first DRTM implementation. It was implemented back in 2007 as an open source project focused on Intel TXT processors only. And it is, to this day, only supporting Intel TXT processors. It does not, nor based on past statements, will it ever support any other DRTM solution. So kind of hit on this a little more detail on this slide. So it uses this exokernel model specifically because SMX requires you to manage the power events. So basically the TBoot kernel is loaded, it's always present. Every operating system has to be made aware that it's running underneath TBoot, so that way it can actually work in conjunction with TBoot for power events. And it is a reentrant kernel. There's effectively, it's two kernels smashed together as one, in a crude way to put it, right? You have a preload, pre-launch segment to it, which is effectively functions as a DCE preamble, and then a post-launch, which is invoked by the ACM, and it functions as this lightweight DCE. So you can refer to it as either a late DCE or an early DLME. And it can be used as simply an OS loader, i.e. it doesn't have to have a kernel that's aware of it, but based on documentations, and as I pointed out, you run the risk of crashes during power shutdowns because the power events won't be handled properly. It does require the usage of a bootloader. It does not know how to be launched directly as UEFI. It relies on the bootloader to call EBS and pass that information along with it. And as far as I'm aware of today, it does not have any support for the SMI transfer monitor, the STM, or the platform property assessment module, the PPAM, for DMI protection or SMI protection. And now there's the newest kid on the block, although we're tied with Microsoft for that, I think. In TrenchBoot. So for TrenchBoot's perspective, we've been focused on building DRTM across the architecture and across kernel. We have a long history with TBoot, but we need to be able to have a multi-vendor, multi-architecture solution that enables DRTM, and specifically for Linux Secure Launch, it enables it for Linux. So that way Linux, which is a multi-vendor, multi-architecture kernel, can use the DRTM capability across all of those architectures it supports. So where does that bring us in terms of timeline of trying to get Linux Secure Launch upstream? So in March of 2019, after we had been banging at this for almost a year, we knew we needed to start engaging the Linux kernel. And so one of the first things we did was we actually wanted to address the fact that when you come out of a dynamic launch, the system does not look like any other, like a static launch. And so the kernel needs to become aware of this new environment, or this new system environment, system state as it's starting up. And so we needed to extend the Linux boot protocol. So we put out a proposal and immediately got knocked down really fast. After that, HPA was gracious enough to really engage with us and help us find an appropriate solution for what we needed. And that was we initially started as the setup header RFC, which we submitted in May of 2019. After a couple of revisions on the patch or the RFC, then the final patch, the target patch, and then multiple revisions of that. In November of 2019, we were able to get the kernel info patch set merged. And that would allow us to be able to pass the necessary informations across that DRTM launch or through the DRTM launch down to the kernel. So fast forward, we have an approved protocol. We started to build the actual, and we refactored what we had at that time, and we brought the secure launch RFC forward in March of 2020. A lot of back and forth over the, whether or not TPM, how and whether TPM support should be inside of the setup kernel. We tried to work out an approach in October. Unfortunately, we were at an impasse. The solution the maintainers were wanting to do would have required a significant amount of rewriting of the TPM driver to make it capable of functioning inside of this the setup kernel. And so after some discussions with some colleagues, we came up with an alternative early measurement approach that we now implemented. After working through all of that, we then submitted version 2 of our patch set in June of 2021, got a little bit of feedback, released version 3, some internal testing along with, again, a little bit of internal, or some comments. We released version 4, and that's where we're at today. As far as how it all works, I'm going to dive through some of that, but there's been a lot of presentations over what we've been doing for Linux Secure Launch. So you can visit our documentation repository with our presentations page that has all the presentations, or most presentations. If I'm sure there's probably a few that haven't gotten pushed in there yet, covering all of this over this 2-year span or 3-year span. So what is the state of the Linux Secure Launch? So for the DCE preamble, you can use either Grub or the Secure Launch KExec. So Grub there is a patch set in flight to add the slaunch directive provided by the Secure Launch module in Grub. That will allow Grub, that indicates to Grub that it should do a dynamic launch event when going to the identified kernel that it was told to load for that entry. And then the Secure Launch KExec will be an extension of the Linux KExec framework, so that way you would be able to initiate a DLE on supported platforms. So that, as you saw earlier today, there's already efforts being planned around this ability, because KExec is becoming more and more popular as a boot mechanism or launch mechanism. All right, so the DCE is started by the DLE, obviously, as we've discussed, and it's supposed to initialize and measure the DLME, extend this all into the TPM. So on Intel, that's already provided by for TXT platforms with a signed binary called the SNet ACM. And it is the primary DCE for Intel. Again, you can argue whether or not tboot can be viewed as a late DCE, that it completes what's done by the ACM, or whether it's a DLMA. You can argue those points. But on AMD, and so for Linux, that obviously for Secure Linux, that when Secure Launch, that won't be the case. It'll be going directly into Linux itself. On AMD, the AMD secure loader. So again, AMD V systems have a defined secure loader specification. It allows you to write your own solution for this. So TrenchBoot, we have active development on our own open source secure loader that we're calling the secure kernel loader, the SKL, which you've probably seen references again. We used to call it landing zone. That was because we just didn't have a better name for it, and we were just more focused on getting code done than worried about naming things at that time. So we're in the process of transitioning over and getting everything productized, I guess you could say, as the secure kernel loader. That brings us, once you've got through the DCE, that brings you into the actual secure launch, into the DLME, which is, as we explained what the DLME is, that is Linux Secure Launch. That is the patch set that's been submitted to the mailing list, the kernel mailing list. So just kind of walk through what is involved in this patch set. So the first bit is the Secure Launch stub. It has its own assembly code that's inside the compressed kernel. Its responsibility is to transition from the state that the DCE left the system to what startup 32 is expecting and can jump to. As I highlighted, and there's been some discussions about this today as well, the way TXT leaves the system and the way AMD leaves the system, we have control over the AMD side more so. So we're making it look as much like the TXT entry as we can. But the fact is that the state that it's left in when it comes out of that is not anything that Linux would ever expect, especially when it comes to to your APs. They're in a totally different state, and interactions with them are definitely different on Intel as well as AMD. That could result in, if not done correctly, a fault in your system. So the stub is responsible for taking you from that state and getting you to a common state that Linux tends to expect the system to be in. Startup 32 then does its thing, goes through startup 64, and as that completes, there is we do a call into our SL main method. The purpose here is a few things, but just as a quick summary, the major things we're doing is we're locating the TPM event log. We're writing all the measurements of everything that was passed, all the configuration information we got, module information that was passed from the preamble or from the DCE, because you can pass information across just like on Windows. We want to measure all that stuff before any of that information is used. Now, unfortunately, because at this point in the system, there's some bits of information that had to be used before we were able to measure it. If you look in the code, it's all documented what we're missing and everything. During that, a call is made to SL check region, and it does a handful of things. One of the big things that's of concern, or that I wanted to highlight here, is that it basically ensures that if you're familiar with how Linux works, it has a setup kernel and then a compressed main kernel. The setup kernel's responsibility is to decompress the main kernel. Well, we don't want to write that into memory that's not DMA protected. So one of the things we do is we make sure that the identified region that's going to be decompressed into is protected. And it also checks and makes sure a lot of other things are in protected regions and don't collide and these things. But the big thing is that we make sure that the decompressed kernel does not get decompressed into memory that could be DMA'd. At that point, decompression continues, and then we enter into the main kernel. During setup arc, the secure launch setup is then called to verify and finalize the dynamic launch startup. And what that means is that as I highlighted, actually, no, that's a little bit later, I apologize. But it needs to finalize the rest of the way from the dynamic launch startup. also during this time, during the SMP bring up, there's been a slight modification because, again, the APs waking up your processors does not work the same way as it's typically expected. So we had to make sure that the interfacing with the APs to wake them up was handled appropriately. And then our SL platform module is registered as a late init call at that point. And then towards the end of initialization, the actual platform module is called because it's registered as a NIT call, a late init call. And at that point, all those measurements we stashed at the beginning are, I guess I didn't mention that. So when those measurements are taken at the beginning, we stuff them into the log with special markers to let us know where those events are in the log. And at that point, we then take those measurements and actually extend them into the TPM in the locations that they were supposed to be done. And again, the reason why that's all done is because we don't have access to the TPM during the setup kernel. So it's not until we get to the decompressed kernel and we have to make sure that the TPM driver has had a chance to come online and find the TPM so we can then use it to send the measurements to the TPM. And then the last thing it does is it initializes a security FS to give access to the DRTM log, as well as the TXT public registers for when you're on Intel, and any other metadata that might get passed along as we expand this capability. So in a nutshell, that is what our Linux patch set introduces to the Linux kernel. So platform support. So secure launch is being developed that it can be used on traditional BIOSes or UEFI and CSM mode, open source firmware such as Core Boot, or UEFI systems. As far as traditional BIOSes and open source firmware, pretty much works out of the box. You saw there was a table earlier today to kind of highlight issues that have been ran on, but for the most part, we've been good to work on the systems we've tested on. As far as UEFI is concerned, due to design decisions done in the Linux kernel, if you want to launch Linux directly from EFI, they put in what's referred to as the EFI stub inside of the kernel. Unfortunately, this does not align well with the DRTM model, mainly because one of the things I didn't highlight in this discussion is that on TXT, I'm not for sure if it happens on AMD, you cannot make the senter call on an Intel processor without calling EBS first. It will likely crash your system. So the DRTM launch has to happen after EBS is called. Grub has already been made capable of collecting and passing all the whether they're upstream or not, Grub has the capability of passing all that information that the Linux kernel is expecting in the locations the Linux kernel is expecting. These are, the option ROMs. This is as well as the SRTM log. These things can be passed by Grub along over to the Linux kernel through the DRTM. And it also allows us to better align with the security boundaries of the original UEFI model, which was that EBS was supposed to be a delineation between bootloaders and operating systems, whereas this basically allows you're making Linux straddle this boundary. For those that absolutely want to use the EFI stub to start their systems, this is where the DRTM preamble kexec will come in. The EFI stub can do its thing, bring the Linux kernel up, collect all the post-EBS data, collect all the data for post-EBS, and then can use the DRTM preamble kexec to chain load into your ultimate DLME. Basically, the reason this approach is being taken is because it reduces entry points. Instead of kexec is going to have to be able to deal with passing this information along as well, just a standard KExec, not even a DRTM preamble version of it. So whenever that is solved, then we'll have that solution will apply for this as well, and we can make the DRTM, the secure launch, support all that. So upcoming changes. So what do we've got coming along? I've only got a few minutes, so I got to fly through these. All right, so what do we got coming? So we're going to improve based on some comments, we're going to improve the documentation, work on adding the DC preamble, and also start introducing the SMI, SMM runtime protection support. So from the documentation, some of the feedback we got, early feedback we got, help explain why you've made the changes you did, why will Linux benefit from it, and help provide, and obviously we need to provide some background to explain for those reasoning. So we're working on getting a lot of that kind of detail into the documentation so that it can be included into the next revision of the patch set. The pre-example KExec, we've hit this numerous times. So yeah, we're going to work on enabling doing a dynamic launch via KExec. This is the big one. So again, as I started off at the beginning during my rant, the SMI has been always this thing that people have used to beat us over the head, even though ironically and tragically, both AMD and Intel already had solutions for this. It just was met with resistance and non-adoption by the IBVs and the OEMs. So Intel had the STM and AMD had the SMM containerization. Ultimately, I still think from a mechanism standpoint, these two are stronger solutions, and there's some background and details on some of this that is linked below from the Platform Security Summit in 2018. But with that said, we need something that would be adopted. And luckily, on our part, Microsoft came along and said, no, we need something for our secure core PC. So both Intel and AMD have developed a lighter weight reference monitor solution that is available. And luckily for us, Intel has even made the details public for the interface, which, and their use of the reference model is called the PPAM, we mentioned earlier today. The fact is that they basically reuse the STM interface. Whether or not you want to discuss of whether PPAM is truly an STM, a lightweight STM, or if it's just purely a reference monitor, you could go back and forth over those details of what makes an STM. But from the system perspective, it is the STM interface. It's the STM API, and that is already documented, public, and can be used. Unfortunately, AMD's documentation for the implementation is locked up under NDA, which seems to be very difficult to get, at least for me. But once we can get some documentation on that, we will be able to add AMD support for it. So one of the things we'll be working towards is getting support for enabling PPAM from the SL stub. So that a way, when you come, once your launch has occurred and before the SL stub has re-enabled the SMI handler, we will fire off the calls to through the STM interface to enable the PPAM to protect and measure the SMI and provide that information back to us before we enable the SMIs and start the system boot. So in summary, some advantages of secure launch. Again, I kind of hit this indirectly and directly throughout the talk. It brings native upstream DRTM capability for Linux. It becomes a free feature for any Linux-based effort. So Linux boot could then use it to be able to do DRTM launches of the whatever kernel they're booting into. It provides multiple architecture support. There's AMD, Intel, as you saw earlier, ARM's on its way, and we want to support that as well and get that integrated in. And there's even Open Power has a DRTM solution that we want to get integrated and integrated all part of this Linux secure launch. And then, of course, because of the way we're doing it, we're not focused on purely the early launch case, which is what one of the points I didn't really highlight too strongly on the other implementations. Both Windows and TBoot are more focused on functioning in that early launch use case. Because we've built this so it can happen at it is capable of functioning both as an early launch or a late launch, as well as triggering late launches as we were talking about from the K-exec perspective. And with that, I believe I'm just on time. So I got 2 minutes for questions.
So I don't know if you can hear me. This is Kirk Brannick. I'm actually the architect responsible for the PPAM and largely responsible for the STM and probably other pieces of TXT as well. So
thank you.
Pretty well versed with what's going on here. Happy to. I can't commit a lot of time, but maybe you and I should hook up offline at some point and have a chat about how this thing works. I did publish a white paper which is available. I can probably send you the link to that gives some pretty good detail on exactly how the PPAM functions.
Exactly. I use that exact white paper for this, and that's where I got all this understanding.
So there's some key differentiators, I think, in what we did. Right, you're right that the STM approach was very heavy-handed and kind of intractable from a scalability perspective, and that's why it didn't work. Right.
Yeah.
And what we did with PPAM is we changed it up and we said, why don't we just build the platform securely by construction, right? Make the SMI handler deprivilege itself. Mm-hmm. And we added some hardware to assist with that some time back as well. It wasn't just software, right?
Right.
But then the idea was we'd like to be able to prove to a third-party verifier, in fact, that this was done and was done correctly, right? Yep. And so you can actually tell. So what the PPAM does is and that's why we call it the Platform Properties Assessment Module, right? Mm-hmm. It has the sufficient privilege to inspect the SMI handler, and we effectively normalized by signing in a manner of speaking, yep, the entry code of the SMI handler. So when you take an SMI and it begins executing an SMM, it's executing a piece of code that we write and sign, right? And that code will set up the rest of the SMI handler to run deprivileged in ring 3.
Yep.
So instead of using virtualization and VTX to deprivilege the SMI handler, we're using just regular old privilege rings, right?
Yep.
And additionally, it will deprivilege itself, right? So we made the page tables static. We did a number of things, a lot of things, in fact, to harden the SMI handler and make it correct. And so that's all done by construction, and that happens whether or not you do a DRTM. It's just the way the SMI handler is built in one of these machines, right?
Right.
And where the DRTM comes in is when the SNIT module runs after the SCenter event, right? Mm-hmm. The SNIT module will actually measure and create extend an event in the TPM into PCR. I want to say 17. I can't remember 17. Which one, but
yeah, that's the paper said 17.
Yeah, I can never remember. It's like I've done this for years and I can't remember ever. So
yeah.
Doesn't matter, right? We extend it to the TPM and then to the TPM log if one exists, which one should. Okay. And so what happens then is when this primordial launched environment, I forget the term you were using for it, but the one that's launched immediately out of this, when we transfer control out of the SNIT module, mm-hmm. If the platform has been configured to use a PPAM, which is also extended, that state, right? Mm-hmm. The SMI in the platform is actually masked and cannot occur.
Yep.
And so what happens is that this primordial environment can verify a certificate that we provided that's a digital signature over the hash of this PPAM agent that is sitting in SMRAM. Mm-hmm. Okay, so it can verify that the PPAM is as it's supposed to be and is correct before it runs, and then it'll invoke the PPAM using the mechanisms that were originally architected for STM, as you noted, right?
Yep, the VM call.
We didn't need to create new microcode or new hardware to go do this. We just kind of made use of something that was basically dormant and not being used, right?
Yeah.
And it can get back this report from the PPAM about the condition of the SMI handler and what the scope and scale of its sort of privilege is in the system. Can the SMI handler touch your memory? Can it touch various MSRs? Can it touch MMIO, different places? Can it access state save? All these different kinds of important questions that describe the privilege in the system of the SMI handler with regard to the TCB of the environment you just launched with the DRTM, right?
Right.
And so then you can evaluate that answer and then make choices about sealing and unsealing of critical pieces of data before you explicitly go unmask SMI using a different get sec leaf, right? So that's how it's intended to work. So when we call it when you call it a lightweight STM, it's really an STM is three things. It's a policy negotiation mechanism. It is a policy enforcement mechanism, and it's a policy verification or reporting mechanism.
Right.
The PPAM is really only one of those three. It's the policy reporting mechanism. The other two are built into the BIOS by construction. And
that's why I say you could,
that's the way it is. Yeah.
That's why I could always say you could, whether you wanted to argue if what constitutes an STM of does it, right? It does, technically it does all three of those things. Two of them it's just fixed, right? You can't negotiate them. Right?
And to be fair, we decomposed it, right? The PPAM and the entry code that sits at the beginning of the BIOS. So the entry code is the other part, right? That's gonna do the enforcement, right? And that entry code, the hash of that entry code is embedded into the PPAM and it's verified by the PPAM. So they go together, and even though the SINIT doesn't directly measure the entry code of the SMI handler, the PPAM does and checks against its own, known good reference hash. So it is still connected, and in some sense you could say that the entry code is an extension of the PPAM, and in a sense, then it really is an STM in a way. Right?
Yeah. That's why I say, if you look at the interface, it uses the STM interface. So if it's a duck, if it quacks like a duck, then it's a duck, right?
Right.
But no, right. When you get down to the details, right, it is nuanced, right, and it is not an STM from when you want to get nuanced.
No, it's not. But I agree, I'm super happy that Microsoft, we were able to work with Microsoft and get them to pick it up, right? It solved a problem for them. Getting STM, sort of classic STM enabled in the ecosystem was going to be a hellacious lift that probably was never going to happen, right? And so, and like I said, the other benefit we got about doing it this way is in a classic STM sense, you only ever got that isolation and protection of the SMI handler if you did a launch of the STM, which meant that it was, unless you were doing that, it wasn't doing anything.
Right. Right.
And unless you were doing TXT, you had no proof that it was done right. And it's a long thread, but anyway, so I'm more than happy to try to help you guys out as best I can, right? So if you got questions, shoot them my way, and I can.
Definitely. So there is the VPub afterwards. I'll flip over to that slide. So
I'm not sure I can attend though. I'm sorry, but
okay. All right. Well,
I'll reach out one way or another. I think you were the one that was commenting on Twitter the other day, I think.
Yeah, with the I'm the face behind the TrenchBoot Twitter account. Yes,
that's what I thought. So I can message you over that, and we can get hooked up to have a chat. So
yeah.
Can I ask one quick question, Daniel?
Sure.
So, Kirk, apologies, but since you're an Intel person, I don't get to ask this question too many times, but I used to work for Citrix, and Citrix had Intel had sponsored Citrix to do the early TXT support in Zen Client. That was like 10 years ago. So I spent like two years interacting with lots of Intel people and the vPro team. But, so since then, one of the challenges has always been getting hardware. And there's been, I think, some TXT support in one Atom SKU, like a Tremont SKU that's used for 5G base stations. And we were really hoping desperately to get, one consumer purchasable Atom box, for example, for routers. Like it'd be extremely valuable to have TXT and now PPAN in a small router, because, routers are extremely targeted devices. So I don't know. It's just maybe it's not something you can talk about, but
I'm not sure I heard a question in there. What I think I heard was an observation that not having TXT top to bottom is a problem.
Well, we've talked to some Intel people who promised us that we were going to get an Atom box, and it just never happened. So I'm just wondering why it didn't happen, because it's clearly possible.
I'm not sure I'm the right person to answer that question. What I can do is, I obviously heard this before, and we hear it all the time. There's obviously marketing considerations and on and on and on it goes, right? So I've always been a big fan of open source and trying. I'm not well versed in open source, but I like the ethos of it, right? Mm-hmm. But I don't think it's a solution to all problems either. But as far as what products end up with which mix of technologies on them, that's an interesting machine that causes that to happen, for some definition of the word interesting. So
I guess along those lines, the one thing I would ask is that, because as you were pointing out, and one of the things I noticed is that PPAM is definitely not tied to TXT anymore, right? It can just be on any system. So are we going to, because after I found it, I've been going and looking at the ARC, and they're not even listing it as what CPUs have the capability. So is it going to be ubiquitous, or are we going to be a vPro thing?
Currently, in platforms that you can buy right now, I think you will discover that it is still tied to TXT, because if you try to run it outside of TXT, while it will get invoked, it will complain and say, I need to be used inside of TXT.
Okay.
And these are related to what class of platforms typically make use of this kind of technology.
Right.
And typically they are business platforms. And so we're trying to, what you end up doing is trying to segment things where they're going to be used, and where it makes sense. And you see Microsoft do the same thing with the OS. You don't buy Windows Home and get support for a secure core PC. Maybe you will in Windows 11. I don't know. Yeah. Right. But you see, you see segmentation along those lines, right? And I would say, I can't say anything, but I would say watch this space, right?
Yeah. So I guess let me ask you this, and again, I don't know if you could answer it, but if I were to just go grab a 10th gen board, I happen to find a vPro 10th gen board, will it be there?
It should be. It depends on, I suppose, not if it's really a vPro board. If it's labeled as vPro, yeah, it should be there.
All right, excellent.
It should be there. There is, and if you look at the white paper, you can kind of see where there's some generational differences, but those are largely around the policies that we were implementing and coordinating with, working with Microsoft and it's been an interesting experience getting SMI handlers that, the great unwashed collection of SMI handlers that do all kinds of evil and crazy things to behave better, right? Because they did all kinds of things because they could, right? They had God power, they do whatever they want. And so why not? What's the most expeditious way to ship your platform? I don't know, hack something in. And that's what happened all over the place, right? And so a lot of this has been trying to herd those cats into, better behavior in general. So there's usually other ways to write that software so that it will not be invasive or obtrusive to a dynamically launched or OS software in general, I should say, right?
Right.
But that takes time, right? So we've been sort of taking one bite at a time, trying to get that done, right? Generationally is how it's been going. So it's been going pretty good, right? And I don't know how deep down down the product stack, it will happen. I think if you go buy the lowest end PC you can possibly find in the consumer space, you're probably not going to have any of these benefits, right? You're going to get what
on Intel. No.
Yeah. Well,
so if you want to get an Intel router with TXT, you have to buy a Lenovo 1 liter Tiny that has a PCI slot, and then you can put a Broadcom quad port NIC into it, and then you get the pieces.
Okay,
I have
all right. Point taken. I don't know what you want me to say.
Yeah.
No, I'm saying it's possible. It's so important that people will spend a fortune. They'll spend equivalent of 5 routers to get one Intel-based router with these important features. That's what I'm trying to say. It's not about cheapness. It's about, can I physically give you as much money as I want? Can I buy it at all?
All right. It's good feedback. I'll bring it back. See what, you never know what happens. So anyway, it's been a fascinating conference to kind of just eavesdrop on. Good to hear.
I'm glad you found it. So hopefully.
Yeah, if you didn't harass me on Twitter, I don't think I would have.
Hey, Kirk.
I wasn't trying to harass you. I'm just trying to bring attention to your capability.
I mean, harass in the best sense, right?
Yeah. So. Okay. Yeah.
Say, Kirk, before you run off.
Yeah, go ahead.
If you happen to see Jim Cole, tell him Dr. Greg says hi if he's still around.
Oh, he's still around. And he's my former boss, in fact. James Cole?
Yeah.
Oh, yeah.
Yeah, you and I and he talked a couple of years ago about all this stuff.
Oh, did we? Okay.
Yep.
Okay. Well, this is actually a pretty small world when you get down into this into this space, right? There's not that many people who who care.
15 of them, I think, by the participant count.
Yeah, that's up 20% or something.
Anyway, send my best to him.
I will.
All right. Any other last questions or discussion points, or if you can, we can move on to the VPUB.
Daniel, maybe you should comment on when next you might have an event like this. Is it like in a year from now, in 6 months from now? What do you think? Have you thought about it?
Haven't thought about it. Probably try to do it in another 6 months.
All right. Thank you.
Okay. If not, thank you, everybody. And hopefully we'll see all of you at the VPUB.
The URL is vpub.thesharo.com, right?
Yeah, that will take you to the information page that'll tell you all the connection details.
Okay, thanks.
Yep. All right. Thank you, everybody. It's been a wonderful day.
Bye.
Bye.